Ja. Då ska ni vara välkomna till dag 2 av APRI 10s webbinarium. Igår så fick vi ju en uppsättning presentationer som i huvudsak omfattade då fenomen och insikter och frågeställningar kring förloppen i reaktortanken under ett svårt haveri. Det rörde quenching och återsmältning, genomsmältning av reaktortanken och vidare då så fick vi presentationer om när det gäller svåra haveriers kemi, om tellurs roll och betydelse från Chalmers, samt då en presentation av RAM-metodiken, hur läget var med den. Och det här fortsätter vi med nu under dag 2 med frågeställningar kopplade då till fenomen, insikter och förlopp även efter genomsmältning av tanken. Dessutom då så ska vi få en översikt över de internationella projekten som rör svåra haverier och de projekt som vi i APRI 10 specifikt har bevakat. Avslutningsvis då så får vi en presentation av vår inbjudna huvudtalare som ska berätta om Fukushimas tankgenomsmältningar och en kort blick mot APRI 11. Det är väl matsedeln för dagen. Jag hoppas att det kommer att gå lika bra som igår. Så ha det så bra. Jag lämnar över till moderatorn då, Roberta.
Thank you, Marit. So welcome back everyone for day 2 of APRI webinar, and we will continue now with all the presentations from NPS research, and we're going to start with Mohsen Hosseini. He's going to talk about investigation of melt float infiltration in porous media. Before we start, just remember you can write comments on the chat when you go to the YouTube homepage. You can write questions there. So do that during the presentation so I can have them when Mohsen is done. Then I can then we can ask the questions more efficiently. So do write questions during the presentation so I can then ask Mohsen. So Mohsen, are you there? Can you hear me?
Yes.
Ready with your presentation?
Start sharing. Yes.
So go for it. The floor is yours.
Thank you. Do you see my presentation now?
Not yet, but it will come.
Okay.
There you go. Now I see it.
Okay, thank you. So, good morning, everybody. I'm Mohsen Hosseini. I'm going to talk about investigation of melt flow infiltration in porous media with a focus on the effect of wettability and thermal property. I'm going to start with some introduction, then I will continue with material selection study, which was the basis for our study on the effect of wettability. And then we continue with a number of experiments which were devoted to see this effect, which was numbered E16 to E20 in MISPAT facility. So we will start with experimental setup, and we see the effect of wettability and thermal property as we have seen in the experiments. And we will, I will end my presentation with future MISPAT test and the outlook. So MISPAT is actually representing multi-component remelting, relocation, and solidification in porous debris. And why this is important, because in the late phase severe accident scenario, there might be cases that corium melt, relocate down, and creates a porous debris as demonstrated schematically here. So this porous debris basically is composed of both metallic and non-metallic phases or oxidic phases. So at elevated temperatures around 1200, let's say, there is a possibility for the metallic phase to melt or remelt and create a pool and then relocate inside the porous debris of oxidic material, which are still at solid state. So actually the importance of this phenomenon first was identified by the previous Raspla and Masca experiment with prototypic material. And they found that at the end of heating the prototypic corium to 1200 level, let's say, some metallic phases were found remelted and solidified at lower regions. So this can actually happen, but there is currently a poor knowledge on this mass transfer. So we don't know about it a lot. So this actually resulted in simplification of severe accident models. But we know that the effect is significant on the vessel failure mode and timing and initial conditions for ex-vessel accident progression. So based on the result of the Masca, we know that the effect of wettability is important because in that report, the effects are mainly connected to the effect of wettability. What we don't know is the kinetics of the melt flow because we don't know what happens in terms of flow kinetics inside the porous debris. So for that, we identified the need for further experiments to study in more depth the effect of wettability and thermal property with different range of affecting parameters. So yesterday, my colleague, Dr. Komlev, provided a presentation with CIMECO 2 facility. There, we can say that this effect is, this test facility is connected to integral effect test to study the effect of dry out and remelting. And for MISPOT, which I'm going to represent today, actually we are concentrating on separate effect studies on the melt infiltration inside the porous media. I'm going to give more details in the following slides about the test facility. So basically the study of melt relocation and infiltration started with Remcoat facility first, which the schematic diagram is presented here. So it is a rectangular geometry, as you see here, and the dimension is written here, 41 centimeters, relatively small, but it was also interesting regarding the initial understanding of the phenomena. Because it has key feature of visualization. Basically what we did, we filled columns of particles in rectangular form and we provided melt at different temperatures of the porous debris to see the effect of melt infiltration. Although it was interesting, but it has some drawbacks like large heat losses, like poor control on the environment and so on. So we decided to upgrade our design to MISPOT facility, which is represented on the right figure. As you see here, it's a quartz tube, cylindrical quartz tube with 120 millimeter in the test section diameter, which is much bigger than this one, which is 20. So with this, we managed to minimize the wall effect. We had better control on the working environment and boundary conditions. And we have improved the large heat losses, which was one of the problems. And the leakage problem, which was identified in Remcoat, was resolved in the new facility. Here is the overview of the Remcoat test series. Actually, the details are provided in this reference as I written here. But to have a quick look, we have performed 15 tests in that setup, and each one represents a series of tests, 3 to 4 tests. And first tests were devoted to exploratory tests, and later on we added step-by-step features to them, like heaters, force sensors, additional thermocouples, and so on. And for all of them, we have for the first series up to E7, we used tin as melt simulant material, and then later on we used tin bismuth as the tin bismuth eutectic as the melt simulant. And then as you see here, we filled up with different particles with different morphology, spherical and non-spherical, with covering a range of porosity, hydraulic diameter, and so on. And the phenomena which we considered was actually listed here as you see melt penetration depths in some of them, melt infiltration, and also remelting in only E10 experiment. So this is the specification, technical specification of our test facility. As you see here, we have a tube furnace, a vertical tube furnace with 3 heating zones. And basically, we fill up particles in some regions, and it is 280 because of some technical reasons. If necessary, I will elaborate more. But it has each region has its own independent heating system or with PID controller, and each one can provide 3 kilowatt of power. So basically, we fill particles here, we heat them up to the certain level as the target temperature, and then we start pouring melt to see how melt infiltrates inside the porous medium. So first we try to select candidate materials to have a good picture on the wettability. For that, the ideal goal was to have 3 representative cases: wettable, slightly wettable, and non-wettable conditions. And wettable conditions means that if you put a drop of that melt on top of a substrate of the same material that we use in the test of porous debris, then it creates a contact angle less than 90. A slightly wettable conditions is connected to contact angle around 90 degrees, and non-wettable conditions is connected to contact angle above 90. So for that, we have selected 5 candidate materials: copper, stainless steel, brass, aluminum, and nickel, which with different thermal property, as you see here. For example, copper has 400 for thermal conductivity, and the lowest thermal conductivity is for stainless steel with 14.8. And this thermal diffusivity is covering a range from 3.8 to 160. So we did 2 series of this. The first series of tests was to have a qualitative assessment of the angle of contact between the melt simulant and the material that we use for the debris. So we created a pool of the melt at the temperature, the same condition as the REM-code experiment or MISPOD experiments. Then we inserted a rod inside the pool. This technique is actually called wetting balance technique, to see what will be the angle of contact between the liquid phase and the solid phase. We did the same for all. For example, copper here shows better wettability, as you see here, than stainless steel. Then we had second series of tests, which was called CT, which represent complementary test, W2O, which is the second series. And we basically, what we did is to provide the same conditions as the large scale MISPOD test, but at a smaller scale with the same test conditions regarding temperature of the debris and temperature of the melt and the melt pool height and so on. So in addition to that material that I've listed in the previous slide, we had also tried surface treatment of copper particles. First surface treatment was tin coating, and the second surface treatment was oxidizing of the copper particles. So with this, we try to mimic the test conditions of the real MISPOD test in our small scale test, which has a 10 centimeter length and 4 centimeter diameter for the quartz tube. And we poured melt to see how different melt penetration will be in different cases. So actually, to provide a systematic experimental survey on the effect of wettability, other affecting parameters should be ideally isolated. But this is a very challenging test because wettability of the material is not independent from other things, and most importantly from the, let's say, thermal property of the particles. So for that, the best solution was found to use similar material but with different surface treatment. And this is what we have finally picked as our candidate material. So for the case of weak wettability, we consider the stainless steel. For the slight wettability, copper particles, and the same material were coated with tin to provide a good wettability conditions. So basically, the thermal property are similar for tin-coated stainless steel and non-coated stainless steel, and also for copper and tin-coated copper particles. So with that, we started the 4 tests on the effect of wettability and thermal property. So test E16 is done with copper particles. All of them have, as you see here, from E16 to E20, all of them have the same size. And also the test conditions are similar regarding the temperature of the debris and temperature of the melt simulant. And the only difference is the material. So E18 is the same copper, but with tin coating this time. E19 is stainless steel, and E20 is stainless steel tin coated. So based on the results, we expect that the effect of wettability could be understood in more depth, comparing the results, let's say, for E16 and E18, and also E19 and E20. And since E20 and E80 both are tin coated, so they have similar surface properties, but the thermal properties are different. So the effect of thermal property is expected with comparison of these 2 cases. And this is the schematic of our test. As you see here, 28 centimeter is the depth of our porous debris, and these are representing our heating zones, and we heat them up to 125 as the target temperature. So we will create a uniform axial temperature along the porous debris. Here is the test matrix for MISPOD experiments. Actually, I'm going to talk about 4 experiments which are highlighted here, but in addition, we have also studied effect of axial temperature gradient with other tests. So here we have put E16 with copper particles as our reference case, and E18 to E20 tries to mimic the same test conditions for E16. This MISPOD facility has advanced measurement techniques. So one of them is using FPG for melt pool level measurement, which represent fiber Bragg grating or optical sensors. And also the other set of FPGs for melt front identification inside the porous debris. And we use another FPG for boundary temperature measurement. And also we equipped our test section with laser sensors in order to have a record of melt pool level kinetics on top of the. So we have diverse methods of the measurement in our test facility. Here is the experimental setup. We used, as I said, 1.5 millimeter spherical particles. We created uniform temperature in the debris, and the debris height was 280 millimeter, and the melt simulant was tin bismuth eutectic for all of the tests, and all of them had the same 300 degrees of Celsius at the time of pouring. And the initial melt pool height was similar, 15 millimeter. So as you see here, here is our furnace, and we use IR camera for temperature measurement on the periphery of the test section, and also different cameras looking at different angle to our test section. In addition, we have this laser device on top, which shows the melt pool build up and melt pool decrease on top of our test section. So here is the axial temperature profile in our debris. This is the reference case E16, showing this. This line shows the temperature at the center, and also at the side with this the black dots, and also with triangle, which show somewhere temperature between the center and the wall. So we can see that at the end, quite similar, quite uniform temperature conditions were achieved. So we also successfully reproduced temperature conditions for other tests. So actually, the temperature difference is in the range of 5 degrees of Celsius from the target temperature, which is represented with dash line here. As you see here, the temperature inside debris is lower than the temperature of melting or the melting of our tin bismuth. So we can say that our debris is considered subcooled in comparison to the melting temperature of tin bismuth. So here is the result for E16 test. As I said, E16 is performed with copper spheres. So what we see here is the snapshots of the test at the before melt pouring and while melt pouring and while after melt pouring is finished. So we can see no trace of the melt on the periphery. So it means that melt penetration is completely central. So we cannot have any visual data, but we can rely on our advanced measurement techniques. For the first time, we use FBG here, and we put the data from thermocouple and FBG together, and we see that they have good match together. And also one interesting thing is that we can also identify the lateral movement of the melt based on the location of the thermocouples at the radial location of thermocouples at a certain level. So we can see how long does it take for a radial movement of the melt from one central position to periphery, let's say. And then the other interesting thing is that there is a good match between the data coming from thermocouple and also data from the video, because we had also only just one spot of melt, and we put it in the curve, and we see that there is a match between the data of video and thermocouple. Here is the result with tin coated copper particles. So again, most of the melt penetrated, and the remaining are in the form of splashes remain on the top quartz. But again, there is no melt trace on the periphery. But thanks to the instrumentation, we could capture the kinetics of the melt flow inside the test section. So data from FBG and thermocouple are matching well, and this is the final penetration depths which were observed at the end of the experiment, and this is the final obtained by our instruments. And E19 with stainless steel spheres, again, most of the melt penetrated with no periphery trace on the quartz wall, but we captured the melt penetration kinetics with different instrumentation that we have used. So the depths of penetration and time is shown here with different measurement instruments, FBG, central thermocouples, radial thermocouples, and boundary FBGs. And E20 with tin-coated stainless steel particles, which is the representative case for good wettability. Again, here we see penetration of most of melt in the test section with no trace on the periphery, but again, we can rely on the data coming from the instrumentation. But this time, melt penetrated the whole way down of the test section, and at the end, it leaked out from the bottom. So we can see that drops frozen at the bottom of our test section here. So after that, we dismantled the test section, we removed the particles, and we preserved the final ingot. This is the shape of the final ingot. So with copper particles, we got a pear shape. We call it pear shape. And with tin-coated copper particles at similar conditions, we got another different shape. We call it carrot shape. Again, for stainless steel particles and tin-coated stainless particles, we see the same effect. So based on this, we can say that the effect of wettability is strong in the case of melt infiltration. So a few words about the melt penetration kinetics. So based on the melt penetration kinetics that we obtained from the experimental data, we have observed consistently two flow regimes inside the porous debris. So we have seen that at the beginning, for the early time period, we have a parabolic regime. So we have a linear relation between depth squared and time. And later on, it deviates from this linear, this parabolic behavior, and it falls in a linear regime. As you see here, there is a linear connection or really linear relation between the melt depth and the time. The same is also observed for tin-coated copper particles. Also, we have data starting from E18 for the laser, so which shows what is the melt pool buildup, melt pool level buildup, and melt pool level decrease after end of the melt pouring. So basically, we also see the this parabolic and linear regime. Here, the parabolic regime we connected to the competition here. The competition between the capillary and melt pool head, and also this gravity regime we connected to the competition between gravity and capillary regimes. Basically, there is a time for the transition from one regime to another. So for tin-coated copper particles, we obtained 35 seconds. And for E16 with non-coated particles, we obtained it at 14 seconds. So it means that we are longer at a longer time at the capillary regime for the case of tin-coated particles. The same result for E19 with the stainless steel particles. Again, we see this two-flow regime at the beginning, parabolic regime, and then later linear regime. So, but the gravity-driven regime, as you see here, is much slower. The rate of melt penetration is much slower in the case of stainless steel in comparison to copper particles. And E20 with tin-coated stainless steel particles. So again, we see that parabolic and linear behavior of the flow with the transition time, which is much longer. That is 71 for the case of stainless steel, but for the case of tin-coated stainless steel is 32, which is comparable with the case of tin-coated copper particles, which was 35 seconds. And at the end, we conclude that the MISPOT experiments on the effect of wettability E16 to E20 have been performed successfully under the condition of the uniform temperature or nearly uniform axial temperature inside the porous debris. And in all cases, most of the pore melt penetrated inside the bed. Melt penetration was central with no periphery, and advanced measurement techniques actually successfully identified the melt front position inside the porous debris. And we identified two flow regimes, as I said, capillary at the beginning and later gravity-driven regime, which is a competition between hydrostatic head, gravity, and capillary forces. And we can, as I showed in the ingots, we see a strong effect of wettability on the final shape of the ingot and on the melt penetration kinetics. So we think that extension of database would be needed for future model development, because already we have data on two material. It might be better to have also for, especially for non-metallic particles, similar test to see the effect of thermal property and wettability. So at the end, one good question would be, what is possible impact of this experiment on the reactor safety? So for that, actually, we can get much better speculations after development and validation of the models, because in that case, we can understand better the mass transfer of the metallic phase inside the oxidic phase or porous debris, and we can connect it to thermomechanical effects and later to the failure mode and timing, which is very important, which provides also a boundary condition for the X vessel. But we can look at the problem from the X vessel phase point of view, because in the X vessel case also there could be cases for debris dry out and remelting. So then the results coming from the MISPOT can also provide a good basis for this kind of calculations. And also we are continuing our experimental activities and our simulation activities. First, we are doing some work on model development, and it's under progress. And further experiments are also ongoing for extension of the database, as I said, for the effect of wettability and thermal property. And also we are in collaboration with other KTH departments. We are trying to provide a precise wettability measurement with a sessile drop method. And also some interface composition analysis would be very beneficiary. For example, using EDX analysis and so on. And at the end, I acknowledge the support from NRA, Nuclear Regulatory Authority of Japan, and APRI for this project. Thank you. That's all for my presentation.
Thank you, Hussein. We already have some questions for you. Thank you for the presentation. Let me see here. Patrick Isaacson from SSM would like to know if this kind of experiments for similar experiments or this has been done before, or this the effect of wettability on debris in the penetration of the melt, if this has been studied before, or if this is a novel research.
Actually, it's novel, so we can call it first of a kind in this area. We cannot see a lot in this area, but it is of interest of, as I heard from from other research organizations, that they are also very interested in doing something like that. But I can say that this is the first one in this area.
I have a question, because in the actual tests you use tin with the same initial temperature, the temperature before pouring. What is your feeling about if you use a higher melt superheat? Would that affect, that would surely affect the penetration, but I wonder if that effect will be even stronger than the wettability effect.
Actually, we have in a REMCode test, the first, as I showed in my first slide, in the REMCode test with slice geometry, this test. We have studied that effect. So based on that result, we can see the effect of melt superheat is not strong in comparison to others. Effect of debris temperature is much stronger than the effect of the melt superheat in the studied range. The area that we also concentrated, also, as I said, in MISPOT facility, one of the areas that we have covered is the effect of axial temperature gradient, and it provided a very interesting result in case that with a little bit different axial temperature gradient, we can see totally different behavior on the shape of the ingot and also the melt penetration dynamics. And this can also be connected to some extent to wettability, because at higher temperatures we have better wettability as well.
Was that the problem with the other facility? Was that you had the wall effect, that it was a lot of some of the melt was pouring, finding a bypass? Is that what was that? I don't remember. I think it was something like that. Was it?
Yeah, actually, it was good start, but it has some drawbacks. First of all, as I showed, the size of the test facility. Here, as you see, the size is small, so we have a 20 millimeter between the front wall, which we see here, and the back wall, which is on the other side. So the wall effect could be strong, especially for the cases that we use large particles, like 6 millimeter particles or so on. This is one of the drawbacks, and the other was we couldn't have a good temperature control on the debris. So and also we had large heat losses, especially for the periphery areas. These compartments which are on the close to the wall, adjacent to the wall of the test section. So these things was the problem. And another, as you said, there was leakage from one compartment to the neighbor compartment in some cases. This was another drawback. So for that, we tried to have a better one, MISPOT, which actually resolve all these issues.
Okay. Just going back to the melt superheat. Well, in a way, if you have a very high temperature, debris, you're heating up your melt, right? As it pours down, as it penetrates. Is that how it works?
Yes.
Yeah. So if you are having high temperature on the debris, you're giving also more heat to the melt, and that makes it more fluent, and then it can penetrate deeper. So the higher the temperature of the debris, you have more penetration. That's what you see, right?
Yeah, exactly. That's a good point, actually. Actually, for that, we should consider, I think the melt superheat or debris superheat is not cannot be considered the only parameters. So for that, we should consider the whole system. I mean, the heat transfer between the melt and the debris as the solid phase. So for that, actually, we could look at the difference between sensible heat of the melt and sensible heat of the debris to rise up temperature to a certain level. Yeah, exactly. So with that, we can also see a connection. So we have also some calculations for that, and we see that with the decrease in this difference between sensible heat of these two phases, so we can see a trend of decreasing of the penetration depth. So penetration depth actually can be connected to the difference in this sensible heat.
Yes, that's what I was coming to. Thank you very much. Oh, well, we have time. You guys have been great with the presentation, so we can ask a lot of questions. In the beginning, in the first slide, you show this like classical picture of the melt inside there. Is this mist pod would be in the late phase where you're going to have a dry situation in the lower head or a wet situation in the lower head? Because if it's a wet situation, I would believe that some steam would go through the debris beds and that would also have an effect on the melt penetration.
Yeah, exactly. But here is the focus area are on the dry conditions. But as I said, SIMACO 2 is considered the case of also debris dry out. So this one is also studies to some extent the same phenomena, but actually what I can say is that my story with mist pod starts when the story with the SIMACO 2 ends. So after dry out, we consider these conditions for mist pod.
Thank you very much, Tim. Sorry for all the questions, but it's interesting research. So
thank you so much.
Thank you very much.
Yep.
We'll soon welcome Roshan Bian, but before that, I just want to remind you, if you're having trouble to write on the chat of the YouTube channel, you have to access the YouTube homepage by the APRI homepage. If you go to apri.se Webbinarium, there is a little thing on the side that says chat. And if you start your YouTube from that, you can automatically write in your chat. If you just open by YouTube, then you have to create an account. So just to remind you, you can always, the easiest way to access the chat is to start YouTube by the APRI homepage. Okay, so we're going to continue with Roshan Bian. Can you hear me?
Yeah.
Are you ready there? He's going to present to us high fidelity simulations of an internally heated molten pool. Can you hear me? And yes, I can see you. But I cannot hear you.
Can you hear me now?
Yeah, now I can. Yes.
Okay. Perfect.
So you have the floor. Please do start your presentation. Thank you.
Thank you. Yeah. Hi. Good morning. And today my topic is high fidelity simulation of an internally heated molten pool. And the slides falls into 5 parts, from the introduction to the conclusions and outlook. First, we'll talk about the background and the motivation of this work. As we all know, in the scenario of severe accident in a nuclear power plant, the reactor core can melt down, and the component inside the pressurized vessel can melt down and relocate it to the lower head of the vessel. And due to the decay heat inside the fuel materials, it will further melt down and formulate the molten pool. And one safety strategy in the design of the nuclear power plant is called in vessel retention of the melt. When this core meltdown accident happened, external cooling are performed to cool the vessel down and to retain the melt inside the vessel, prevent the release of the radioactive materials. And but it's very important to identify the heat flux imposed along the vessel wall from the melt. And if it's higher than the critical heat flux, this strategy won't success. So the analysis of the thermofluid behavior of the melting pool is very important. Here you can see a two-layer model. On the top is the metal layer with smaller density, and at the bottom is the oxidate layer with which are relatively denser, but with heat source inside it. In this case, we are going to consider only the oxidate layer, only a homogeneous molten pool with internal heat source. And due to the heat source inside the domain and no external force imposed on the molten pool, so the heat transfer mechanism within the molten pool is internally heated natural convection. So the flow motion is mainly propelled by the buoyancy force because of the density difference, and the control parameter for such heat transfer, Rayleigh number and the Prandtl number. On the right corner, you can see observation in Bali experiment, also experiment on the homogeneous molten pool by using salt water as the simulant. And the domain, the flow structure can be divided into 3 parts. Here you get the insight, and I will explain it more specifically by using my own results. And lots of experiment, except from Bali experiment, has been conducted on molten pool simulation, including COPO 1, 2, Bali, SIMECO, Life, IPOCO, COPRA, and beside this, now a new facility called SIMECO 2 is being built at the KDH, and the slab type vessel facility, and the radius is 0.5 meter, and so it has a transparent wall at the front and back to visualize the flow structure during the experiment. And the design Rayleigh number for this experiment is up to 10 to the 14th, and from the number, and this is 3.11. So a lot of experiment has been conducted on this case, in this case, but each experiment requires a lot of money and human resources, and designing and conducting experiment can take maybe several years, and it's also a limitation on the materials. The simulant materials, the Prandtl number of them are relatively higher than the prototypic current pool, which is 0.5, but in the experiments, they are all higher than 3, so it's hard to find the proper simulant to simulate the oxidate pool with the Prandtl number of 0.5. And so conducting numerical simulation of molten pool is being encouraged in recent years. And but one thing man has to consider is that because of the high Rayleigh number, there's intensive turbulence inside the molten pool. So how to model the turbulence inside the molten pool is one of the biggest challenge in this case. And as for the turbulence models, there are several choices from runs to NICE. Runs is Reynolds average Navier-Stokes equation. Take average of the momentum Navier-Stokes equation by Reynolds decomposition. And LES is large eddy simulation. You only resolve the large eddy inside the domain and model the small eddies by using the filter. And DNI's direct numerical simulation without any assumptions, but just to directly simulate the whole flow domain. As you can see here, RANS is well used in industrial area because of its consume the least computational resources, but it has the most approximation, so it has a lot of limitation on relatively more complicated phenomena. And less than DNS will request more computational resources, but it has higher accuracy, especially DNS. It requires the most computational resources, but has the highest accuracy. But until now is mainly used in research field. But as the rapid development of the computer architecture and the computational resources, so conducting DNS in industrial areas becomes more feasible now and will be more feasible in the future. So in this work, we are conducting high fidelity simulation. So we choose DNS as the method to simulate the turbulence inside the molten pool. Therefore, DNS simulation of homogeneous acidic molten pool is conducted in semicircular slice geometry based on the symmetrical tool facility. And the first aim is to analyze the thermofluid behaviors inside the molten pool. And the second aim is to provide detailed information of the turbulence quantities, which can be used as the reference data in the assessment of other turbulence models. For example, when you one always comparing their numerical result against experiment results, but can only compare the heat flux, temperature on the probes, maybe, but they cannot compare the turbulence quantities. For example, Reynolds stresses and the turbulent fluxes, but the DNS simulation can provide all the information that needed for the assessment of other turbulence models. So the magnitude of the Rayleigh number in this study is 10 to the 11th because the limitation of the computational resource. But it's already a very good start point because high enough to induce the Foley turbulence inside the domain. Let's see the mathematical models. It's based on the Busnik assumption and incompressible Navier-Stokes equation. The variation of density only depends on the temperature. So we get the governing equation. Here's the mass equation, momentum equation. There's additional terms on the right-hand side. Is the buoyancy force term. And at the energy equation, you have your heat source term here because of the internal heat source. And to generalize the question, we perform normalization and by using length scale, time scale, and temperature scale. Here we got the normalized equations. As you can see in the normalized equations, there are two parameters, RA and PR. So RA is called Rayleigh number. It indicates the buoyancy force over the interior force inside the domain. It's the main control parameters for natural convection. It's the larger it is, the more complicated the flow domain. So another control number is Prandtl number, which depends on the materials and in case the kinetic diffusivity over the thermal diffusivity. And as for the turbulent quantities, the Reynolds decomposition are always performed in this case, and one variable can be divided into two terms. The first term is time average terms, and the second term is the fluctuating term. And because this fluctuating, so the time average over the fluctuating term is 0. By using these properties, we perform the average time average on the Garnier equation, then we get the Reynolds average equations. Here you can see on the right-hand side of the momentum equation, there's a new term called Reynolds stresses, and at the energy equation, there's a term called turbulent heat flux. And to identify the intensity of the turbulence, there's another quantity is called turbulent kinetic energy, which is based on the fluctuating velocities. So before the simulation, we performed the model verification based on 4 cases in Gruskin's study, which had internally heated natural convection within a box structure. Here's the snapshot of the velocity and the temperature distribution at the middle planar of the domain. And we also compared the 2 important quantities, one's the overall average temperature and the overall average vertical direction convective flux, and which indicates the symmetry of the heat transfer induced by the heat source. So here you can see it's in good agreement with the Gruskin's value and between our values. I also compared the temperature distribution along the vertical direction, and in Gruskin's paper that these 2 cases are available. So I performed the comparison in these 2 cases. They all in good agreements. Then we come to the molten pool. The discretization of the equation is conducted by using the code like Webb solvents, and it exploits the spectral element discretization, which is the combination of the finite element method and the spectral method. Finite element method, which is very general and can be utilized on nearly all geometries, but the spectral method has the limitation of the generality, but it can achieve in very high accuracy, high order accuracy. So such method combine the advantages from both. So the more general and accurate than the for example, FEM and FDM and spectral element spectral method. So when performing DNS, the mesh is always very important because it has a highest requirement for the mesh. So in this study, I adopted the Shixina study of DNS mesh size for natural convection for the bulk domain or for the boundary layers. You have to calculate the boundary layers and to satisfy the mesh size within it. And bulk, when your Prandtl number is larger, you have to satisfy larger than 1. You have to satisfy the Batchelor scale, which is the smallest dissipation scale for the heat flux term. After the calculation, in this case, the Rayleigh number is 6.54 times 10 to the 11th, and Prandtl number the same as that in the symmetrical 2 experiment. So we calculate the bulk mesh size and boundary layer mesh size. And here you can see the mesh we are using inside in this simulation. And as for the boundary conditions, we put fixed temperature. As I have shown, there's a 2-layer models. You have metal layer at the top. So this temperature is estimated metal layer temperature, and the adiabatic at the front of back, and the liquider's temperature of the materials at the curve wall and the nose gauge for all the velocity terms at the walls. And yes, the code, the equations are resolved by using like 5,000 code, and we have 45.5 million thousands element numbers, but as shown in the previous discretization method, the grid points, total grid points are 45.4 millions, and the times type, the CHF limitation, and so then we come to the resultant discussion. As you can see, here's a velocity distribution inside the molten pool, and similar to the Bali's observation, the flow domain can be divided into 3 parts. The first one is the upper unstable region. Large turbulence eddies are observed in this part of the fluid domain. And in the lower region of the domain, the flow is kind of very weak and is suppressed. As for the descent, along the curved boundary, descending flow observed along the curved wall, and they are known as V phenomenon. And the reason for this flow structure is that you have the heat source inside the domain. You have the hoist planar in the vertical direction. For example, here. Above it, you have cold wall on the top, then have hot wall at the bottom. So the flow is propelled by the buoyancy force. But above it, you have the hot wall on the top and the cold wall at the bottom. So the flow are suppressed by the buoyancy force. So that's the reason they can be divided into 2 different regions in this case. And as the presence of the curved wall, and this has the cold the temperature. So that's the reason why there is descending flow. As you can see in the velocity field, this the intensive turbulence observed in the upper unstable layer, and so we try to identify the turbulent kinetic energy inside the domain, and as shown here, is consistent with the velocity distribution. At the upper unstable layers, the turbulent kinetic energy are strong, and there are also a small portion located along the curved wall at the descending flow, but there's none here in the suppressed area, because the flow here is mainly propelled by the shear force caused by the descending flow, but it's not turbulence. And we can also see the contribution of each component inside the turbulent kinetic energy. Here's the root mean square of the velocity components. U prime is the velocity along the x direction, V prime is along the y direction, and W prime is along the vertical direction, which is the same direction as buoyancy force. As you can see here, this distribution is along the vertical direction when it's about 0.5 the middle of this domain, and they all becomes larger because of the turbulence. But this one, the W vertical term, is the largest among them, so which indicates that the buoyancy force contributes the most to the turbulence here. And at the lower part of the domain, as you can see, they're all small, but U prime becomes the largest because of the descending flow. It's not at the vertical direction, not only at the vertical direction, but also along X. So that's it. And here is the temperature field. So it's also consistent with the velocity field. Because of the turbulence here, the mixing effect of turbulence, the temperature tends to be homogeneous in the upper unstable domain, and the descending flow will bring the hot fluid penetrating the lower part of the domain, and at the lower domain is the temperature distribution is kind of stratified because of the weak flow motion. And together with temperature field, we have to analyze the turbulent heat flux, which shown in the average Reynolds equation in the mathematical part. And as the buoyancy force is it's only on the vertical direction. So we only analyze the turbulent heat flux along the vertical direction, double prime, T prime. It indicates the turbulent effect on the heat transfer. And as we compare one quantity in the model verification, this WT is the convective vertical flux, which indicates that the overall symmetry of the heat transfer. As you can see here, that's the distribution along the vertical direction near the bottom of the domain. The blue line is the overall convective heat flux, vertical flux, and is negative, indicating the heat will be transferred out in this direction. And in the upper part of the domain, the heat transfer is transferred upwards. But on the distribution of turbulent heat flux, because there's nearly no turbulence here, so no effects, nearly zero. And in the upper domain, the turbulence tends to push the heat upwards, and so that's the effect of the turbulence on the heat transfer. Finally, we're going to talk about the heat flux distribution along the boundaries. And here is the heat flux along the top wall, and here's the heat flux along the curved wall. And that's via polar angle. The polar angle 0 is the bottom of the domain, and it's increased. So that's in this trend. As you can see, the heat flux along the top wall will fluctuate. In this case, because of the large turbulent eddies interactive with the top wall. So here you have the large velocity. Here you have the interval between two eddies. The fluid kind of stagnated, so the heat transfer will be relatively smaller than that with at the edge of the large eddies. And as for the heat flux along the curved wall, as you can see, it will increase as the polar angle increased, but with different increasing rate. It can be divided into 3 parts. At first, the increasing rate is very small because of the flow motion there is quite weak, and the heat transfer is mainly relies on the conduction effect rather than convective effect. But after 20 degrees, it's gradually linearly because of the descending flow effect, and above 60 degree, the increasing rate will be even larger because of the combination effect of the descending flow and the turbulence mixing effect. So that's the reason for the profile. In this work, DNS molten pool convection is presented, which you can see a general fluid structure and heat transfer. They are divided into 3 different regions, and the detailed flow structures and also the turbulent quantity distributions are analyzed and with them, you can have a better understanding of the flow and heat transfer phenomenon, and in the end, the heat flux along the boundaries are obtained, and these quantities are important for the assessment of ascites to the IVR strategy. But this is the start point of the work, and in the future, based on this work, we can extend it in several directions. First, one is to increase the Rayleigh number. We are applying for larger computational resources, and which allows us to conducting larger Rayleigh number. Based on the estimation, we can approach the 10 to the 14th, which is the prototypic Rayleigh number of CMACO2 experiment. And we're also going to compare the turbulent models based on the DNS result. For example, the runs, the AHFM, which is also used in this area, and LES, because for the prototypic reactor core, if the core meltdown, and the Rayleigh number can up to 10 to the 17th. So that's too large for DNS. In that large Rayleigh number, we have to rely on the turbulent models with assumptions. But we can do the comparison works, assessment works at lower Rayleigh number. And the effect of the boundary condition of the molten pool can be analyzed, because in this case we put adiabatic from the back wall, but in reality there will be radiation effect, heat loss at these two walls. So that will be considered in the next step. And the two-layer configuration with light metal layer on the top, we simulate them together, and also the cross formation at the oxide layer. In reality, there will be cross formation, but in this case, we don't take that into consideration. And yet, when the things are settled down, we can do the post-test analysis of CMACO2 experiment. And thanks for the supporters. That's it. Thank you.
Thank you. We have some questions already. I have one question that I'm going to mix with Henrik Lenneskog's question. It has to do with the fact I do understand that experiments do not provide all data to verify a DNS model. But wouldn't that still be useful to use to verify your models with, because there are so many tests like that has been done? Would it be interesting to verify your model with the integral tests like live, all these tests that has been done before, as almost like a checkpoint? So you do it as you go. Just one more thing is that putting together with Henrik Lenneskog case, would that be possible to do with the TMI accident? To maybe look at the question, why didn't they get a vessel breach?
I think in this case that for DNS now the Rayleigh numbers in the study is relatively smaller than that in the experiments, but we are going to increase that in the in our next step. So in that case, when approaching 10 to the 14th, then we can, like you said, verify the model by using the experimental results. And also in DNS, theoretically, that if the mesh meets the requirement of the smallest dissipation size, then we can say we can trust the result of the DNS.
Okay, thank you. Patrick Isaacson has a question. He was wondering if this is the first time we use DNS in the NPS. And if so, if there's any lessons learned.
Yeah. As far as I know, the highest reading number previously for the molten pool convection is 10 to the 8th, but 10 to the 11th is already the highest now. So, yeah.
And you think that would create some complications, some issues with the DNS calculations, the model?
I think the only limitation for this is the computational resources. But as for DNS, is focusing on the homogeneous molten pool. It cannot replace experiment anyhow. It's at the very preliminary stage. But I think it's very important to have DNS because even though you want to use other turbulence models, comparing with DNS is a very good way to verify models.
Thank you, Jean-Pierre. Thank you for your presentation. And
Roberta, can you hear me?
Yes, Walter.
Yeah, I just want to add. I couldn't write in the chat about the YouTube and here, so I can say what I wanted to say. Just to quickly say that to answer Patrick's question, that yes, it has been done at the NPS before by Robert Norgaliev and Dean, this DNS. But as Boshan said, it was 10 to the 8th, and it was a unit box. So it wasn't this curved geometry that was done now. So you don't have access to the same thermofluid behavior as it is relevant to a reactor pressure vessel, because our RPVs are hemispherical at the bottom.
Yes.
Not the unit box. Yeah, that's all. Thank you.
Thank you, Walter.
Thank you, Walter. And I think we will hear from Walter soon, but before that, we're going to take a break. 10 minutes break, 8 minutes break, and let's be back around 10:20, please. I'll see you soon. Welcome back, everyone. We'll continue our seminar with a presentation given by Yang-Lin Chen. We're going to talk about debris scalability analysis, modeling validation, and application. Wang Li, do you hear me? Could you share? The floor is yours. Could you share your presentation?
Sure.
There it is. I still can't hear you. Could you?
Yeah, can you hear me?
There you are. Okay.
Okay, thank you. Thank you. I will start.
Yes, please.
Thank you. Good morning, everyone. My name is Yang Li, and I'm a PhD student in Division of Nuclear Power Safety. The topic of my presentation is debris bed coolability analysis on modeling validation and application. This is the outline of my presentation. I'll start with a brief introduction, and then 3 parts of this work will be presented, including the model validation for debris bed cooling simulations, the study on quench of X-vessel debris bed, and the long-term coolability, and finally the summary and future work. First, the introduction. The severe accident strategy of the Nordic BWRs adopt the flooding of the lower dry valve and cool the released molten coolant X-vessel. This strategy involves very complicated phenomena. For instance, the released molten jet would break up and fragment into small particles. Then the particles would form a debris bed. The successful quench of the hot particles and the achievement of long-term cooling is essential to evaluation of this strategy. The debris bed coolability analysis has been studied in our division experimentally. The Pomeco FR facility was developed and used to investigate the friction pressure drops of single-phase or two-phase flow in a porous particle bed. And later on, the facility was upgraded into Pomeco TH facility, which was focused on the long-term coolability of the debris bed. The drought heat flux was measured of the volumetrically heated particulate debris bed here. Valuable data were obtained for these 2 experiments. There are multiple studies on the long-term cooling of the debris bed. However, the debris bed quench, which is the prerequisite of the long-term cooling, lacks the attention. Besides, there is few assessment on the debris bed with prototypical features. There is also a strong need to find a reliable computational tool to study the quench or the long-term cooling of the debris bed. Driven by these motivations, this study has 4 main tasks. 1, to perform a validation of the code mechanistic code COCOMO, and to develop a coupled simulation tool of Melco and COCOMO for the quench analysis of the debris bed. 3, develop a surrogate model in order to perform a quick estimation of the debris bed long-term coolability. And last, apply all the developed tools on the reference Nordic BWR case. I will introduce the code we use in this study. The severe accident code Malcore is widely used by regulators and researchers. It is developed by Sandia National Laboratory. It is a system code with feature of fast simulation like the MAP code. It is integrated with important phenomena models during a severe accident, like the thermal hydraulics, the core heat up, degradation, relocation, fission product release and transportation, vessel failure, and quorum release, quorum behavior in the cavity, etc. The other important code we use in this study is the mechanistic code COCOMO. It is developed by Stuttgart University. It performs the numerical simulation in multi-dimensional. It treats the debris bed as porous medium, and the coolant in either liquid or gas phase is able to penetrate inside the porous debris bed. And the Bowling heat transfer of the particulate debris bed can be simulated. I mentioned that Malcore code has the model to simulate the quorum behavior in cavity. However, I should note that it should be noted that the X vessel quorum considered in Malcore is not permeable. It is not a particulate debris bed in Malcore. Besides, due to the lump parameter consideration in Malcore, the quorum layer is represented by only one temperature for each layer. The cooling of quorum layer only occurs on the surface of the quorum. Well, for the COCOMO code, it is developed especially for the cooling of particulate debris bed. It performs the numerical simulation based on mesh, so more realistic debris bed shapes can be considered. Cooling by the water penetration inside bed can be achieved. Before we use COCOMO code to simulate the quench of the debris bed, we firstly perform a validation of the code against an experiment called PRO. The PRO experiment is a unique large-scale quench experiment of hot particles. In this experiment, the water injected from the bottom of the hot particles, and then the generated steam and the quench front is measured during the experiment. The data is very unique and valuable. We use the COCOMO code to simulate several tests of the PRO experiment. The result is shown in these figures. For example, we use COCOMO code like this. This is the result from the COCOMO code. The blue line represent the generated steam flow rate by COCOMO, and the red line is the experimental data. We can find a good agreement. Also, this is the quench front propagation comparison between the COCOMO code and the experimental data. It's also agreed well. So as a first attempt, the COCOMO code is applied to simulate a defined conical shape particulate debris bed with two different compositions, with or without the consideration of oxidation. We gave an initial conditions for the debris bed and the pool conditions based on our assumptions. This is the temperature distribution at different time, which also shows the quench front propagation. We can see that the quench front starts from the surface and then propagate from the bottom of the debris bed and push to the top center. In our assumed scenario, the debris bed is fully quenched within 1.5 hours. Then we consider the oxidation, but we observe higher temperature due to the massive energy released from the chemical reaction, and hydrogen is generated. Under this assumption, the debris bed may not be quenched fully. So we found that when we perform the simulation of COCOMO, it requires a lot of assumptions. Like we assumed an initial condition for the bed, for the pool, and pressure for the pool, etc. This information is quite sensitive to the result, and this information is actually related to the plant system during a severe accident. So our assumptions may introduce large uncertainties. In order to promote the accuracy of our simulation, we developed a coupled simulation tool of Melcore and COCOMO. We want to take the advantage of both codes, that Melcore is good at the calculation of thermohydraulic or in-vessel behavior, etc. COCOMO is good at the ex-vessel particulate debris bed cooling. So in the coupled simulation, Melcore provides the initial condition of the bed and the pool, also provide the decay power to the bed. And COCOMO simulate the cooling of the debris bed and return the heat transfer rate to the Melcore. Melcore use the heat transfer rate to boil the cavity pool and calculate the thermohydraulic response of the containment. The data exchange occurs at each Melcore time step. The development of the coupling interface requires the programming for the data communication, also for the coordination of time advance. We applied the coupled simulation on Nordic BWR with station blackout scenario. It is predicted from Melcore that the vessel failure occurs at approximately 6 hours after scram. In this figure, this is from the Melcore standalone simulation result. And we can see the red dashed line is the released quorum mass from the vessel to the cavity by Melcore. We can find that total around 300 tons of the quorum is released to the cavity in a very short time, like within half an hour. This is due to the gross failure model of the lower head in Melcore. And the blue line shows the ex-vessel quorum layer temperature. As I mentioned, Melcore consider the quorum layer as one temperature, so we only get one temperature transient for the whole 300 tons. And we can find that the rough estimation shows in Melcore the temperature of the quorum layer is still at very high temperature of over 1000 K after 20 hours. Based on the Melcore simulation result, it provides the information, and we use this information to define the COCOMO, the debris bed in the COCOMO. And we define a prototypical debris bed with a conical shape. This is the cylindrical coordinate. The left boundary is the axis metric boundary, and this is a cone shape. If we spin along the left boundary, and we define the mass composition of the debris bed in COCOMO. Use the data from Melcore, and we use an average temperature of the quorum, excluding the energy loss during the core release based on the Melcore's data. So we gave an initial bed temperature at around 1800 K according to Melcore data. And we define a bed porosity as 0.42. This value has been used in many previous studies, and we use it as the start of our study. And we consider several particle diameter because we need to define a particle size in COCOMO, but it is not provided by Melcore. We there is a concept called effective particle diameter. It is proposed by previous researchers. It is used to describe a complex debris bed with one particle diameter to simplify the simulation, because as observed from experiments, we find that the particle size is all normally a distribution. It's absolutely not a uniform size in experiment. However, we want to find this effective particle diameter, but for the simulation, but we cannot find a uniform formula by very many studies. Normally, people use mean particle size for the experiment. With COCOMO code, we are able to define a profile of the particle diameter for each cell of the mesh and perform the numerical simulation, which makes it possible to study the effective particle size of our simulated scenario of Nordic BWL. It would be very useful for the future studies. And we performed 3 cases regarding different particle size. Case A and B are homogeneous with one particle size, and case C is a distribution sampled from a Faro test. Case A is the particle size with 1.75 millimeter. This is a measurement from a previous D4 test. And case B, 3 millimeter, it is a typical diameter from CCM test. And Faro L31 test is a special one because it is quite close, very similar to our simulation scenario. The Faro test use prototypical core material and it had similar subcooled condition, highly subcooled condition, and similar system pressure with the Nordic BWR scenario in our study. And in our 31 test, all melt was fragmented without any agglomerate. This is the distribution of the particle size from experiment. So we sampled from distribution and gave a profile to COCOMO. This figure shows the comparison of the quench front propagation between the homogeneous bed and the inhomogeneous bed. This is more regular for the homogeneous bed, but it's a little irregular due to the profile of the particle in distribution is inhomogeneous. This figure shows the quenched mass fraction with time for 3 cases, and this is the maximum temperature that the 3 cases can reach. Case A is the blue line, and it shows the slowest quench rate. It takes the more time to fully quench for case A, and it reaches the highest temperature. And compared with 2 homogeneous cases with this blue line and orange line, we can find large particles like the orange line. They are quenched more fast, and they reach the a lower maximum temperature. And this is reasonable because large particles tends to have lower friction and promote the coolant flow. We can see that case B and C are similar at the beginning of the half an hour, but case C slows down later then. And in this table, we can find that in case A, there is a small amount of the debris reaches to more than 2,500 K. While for case C, there is only a small amount reaches 2,200 K. We may have a too conservative consideration if we use 1.75, which is case A, as the effective particle diameter in our simulated scenario. So the effective particle diameter for the quench process of the Nordic BWR in our simulation would be a little bit smaller than the case B, which is 3 millimeter. This slide shows the result of the containment transient. The blue line is the Melchor standalone case, and the dashed lines from the coupled simulation. And they have, for the coupled simulation, they have pretty similar result, and they all predict an earlier time of the pool saturation and early time of venting. This is because in the coupled simulation, all cases are quenched to the pool temperature, so more energy is transferred to the pool compared with the Melco standalone simulation, which predict a higher temperature even after 20 hours. Besides the quench of the particulate debris bed, we are also interested in if the bed remains coolable for a long time. The important criteria for the long-term coolability is the drought. The debris bed is considered uncoolable if the decay is greater than the drought. For this kind of 1D debris bed, there are many widely used analytical or empirical correlations, but it is hard to find a correlation for the 2D debris bed due to the complex flow pattern. We only resort to the numerical code like COCOMO to predict the drought for 2D bed. But numerical simulation is time-consuming compared with the correlations and could not be used like in the lump parameter combined to achieve the fast simulation feature. So there is a strong need to find a model that is able to have a quick estimation of the drought for 2D debris bed. We first performed the validation of the code for the drought prediction. The polemical experiment conducted in our division is used, regarding the prediction of the drought heat flux, there is a good agreement for many different bed configurations, as shown in this figure. So in this study, we resort to develop a surrogate model to predict the drought of a 2D debris bed based on the COCOMO simulation. We propose a characteristic factor to represent multidimensionality, and it is calculated as the drought of a 2D bed divided by the drought of a 1D bed with the same height. The drought of 1D bed is estimated by the Lempicki model, which is a correlation. We run a lot of samples by COCOMO and generate a database to train the surrogate model. In order to generate the samples, we firstly summarize the parameters that may affect the drought of a 2D bed, like the porosity, particle diameter, the slope angle, etc. We calculate this, we then define a possible range and generate samples. We calculate these samples and generate a database, and we use part of the samples to train our surrogate model with a Python package, and we use the other part of the data to check the accuracy of our surrogate model. Here are the model outcomes regarding the comparison between full model prediction and surrogate model prediction. We found the errors are within 10%. The surrogate model would be very useful for uncertainty analysis or risk analysis, which requires a large amount of case study. We could also use the surrogate model to generate a coolability map. For instance, this is the coolability map for the reference Nordic BWR. It is marked in red if the decay is higher than the dry-out, which considered not coolable. And we can quickly spot the debris bed is coolable or not given certain conditions like the slope angle, the porosity, the effective particle diameter, etc. The surrogate model could also be implemented in Melco code with the help of the coupling interface used in the Melco COCOMO coupled simulation. The dryout value is returned to the Melco as a control function value within each Melco time step. For instance, this figure shows the drought of a 2D bed or drought of a 1D bed obtained from the surrogate model. it is and compared with the decay power, this is all obtained from Melchior when the surrogate model is coupled into Melchior. And data can be obtained directly from Melchior, and this kind of data can be used in future studies, like we perform the risk analysis, etc. In summary, we perform an X-vessel debris bed quench and long-term coolability analysis with COCOMO code. Regarding the quench process, the COCOMO code is firstly validated against the PRO experiment with good agreement, and then a coupled simulation, and then we perform a preliminary study, and we found that the COCOMO standalone simulation requires many assumptions, and these assumptions, part of these assumptions could be obtained from Melchior. So we developed the coupled simulation of Melchior and COCOMO, and we use the coupled simulation to perform the safety analysis for a reference Nordic BWR CV accident station blackout scenario. In our simulation, the prototypical debris bed would be quenched within 1.5 hours, with around 11% of the mass reaching over 2000 K. Considering the particle size obtained from the Faro L31 test, and the effective particle diameter for this quench process and in our simulation is suggested to be a little bit smaller than the 3 mm. And it will be found, and it is also found that an early venting time than the Melchior standalone simulation. For the long-term coolability, the COCOMO code is validated against the Pomeco TH test for the drought prediction. Then we develop a fast surrogate model, and this model could be used to perform the uncertainty or risk analysis and or generate coolability maps for the quick estimation. And also we implement the surrogate model like into Melchior by the coupling interface. The future work may include the further development of the surrogate models. We would like to implement more phenomena to achieve the fast simulation for the entire progression after the in-vessel quorum release, like the FCI process, the jet fragmentation, oxidation, etc. And we also want to extend our coupled simulation on the debris bed quench to add some consideration of oxidation, etc. And we also want to consider some effect for the debris bed, like the evolution of debris bed due to the leveling, self-leveling phenomena, etc. So thank you for all the sponsorship, and thank you for your attention. That's all for my presentation. Thank you.
Thank you, Yangshan. We now go for questions. We have some from Henrik and from me. I'll just try to mix. It's a lot of questions. If there is no time to answer, you could do. It would be nice if you could just look at the chat and you can answer some of them. But one of the questions, you use Melchior 1.86, which is the old version before all the Fukushima updates for your standalone cases. I probably understand that the reason for that is that the only source code you have. But it would be very interesting to see this comparison of the standalone Melchior 2.2 with the Melkor Kokomo couple simulation to see if you get close or not, if the results are close or not. Not just comparing to 1.86. I'm not sure if the new version of Melkor will give you a significant difference when it comes to coolability, debris coolability or not. I cannot say, but it'll be very interesting to see also the new version of Melkor in your comparison of the standalones.
Yeah, thank you for the suggestion.
Yeah, that was just a suggestion. Still on this is for a BWR, and I have two questions about that. One of them is that you did a standalone calculation when you have all the melt is released to the wet well directly. So I wonder if this immediate release of the corium in the cavity you did, how would the couple simulation of Kokomo Melkor will cope with a drop-wise melt release? In the case of penetration failure, you're not going to have all coming at once. You're going to have like a drop-wise melt release. With this coupled Melkor Kokomo, how would that behave with that? Is that still possible?
I think it's possible because in Kokomo, we define the particle debris bed on our own. So if we consider a partially release or some other kind, we can define a different kind of debris bed, possible shapes, possible mass, etc. So this is very flexible.
Yeah, I was wondering because if you have a release that is not all at once, your debris bed will change with time. So you'll be adding new debris on the top, if that will create any problem with the coupled simulation.
Unfortunately, the current version of Kokomo we are using is not able to have a debris bed increase with time. So unfortunately, we are not able to deal with that situation. Sorry.
Because that could be more.
Yeah.
Yeah. And I know that Melkor and MAP, you can choose to not have a global vessel failure, and then you will come drop-wise or in small quantities and so on. So that would be very interesting to see if that would be possible to do. But I understand what you're saying, and I would like to couple to the question that Henrik Lennerskog have, how difficult it would be to also use this coupled simulation for a PWR.
For PWR, I'm not. I think the difference mainly focus on the Melkor part. So we have, if we have the Melkor input for the PWR, then the framework is the same. We need to change only the input from Melkor from the BWR to PWR, and then we define a more prototypical debris bed in Kokomo for the PWR. So then it's possible to use in the PWR as well. So the target is not the unique one for only the BWR.
It'll be interesting to test because your debris will be completely different and see if you still have some, if you have different results from the Melkor and the Melkor coupled Kokomo, because you have a completely different debris beds and you don't have such a deep cavity and the fragmentation will be different. That'll be just interesting. You cannot do everything, I understand. Do we have time? We have 1 more minute. Anybody would have any more questions? Okay, I guess so. I will thank you again, Young Lee. We can move to the next speaker.
Thank you so much.
Thank you. And now we we'll hear from Wei-Ning Ma on MISTI experiments, oxidation of metallic melts in water, and quenching of particles and coolants. Wei-Ning, you have the floor.
Yeah, thanks. Share my screen. Okay, can you see? Hello? Hello?
Sorry, my microphone was off. Yes, I can see and hear you.
You can hear me. Okay, good. So before I go to my presentation, let's have a comment to previous presentation. Roberta posed a very good question, actually. Right now, the coupling approach, we just have the fixed breeze bed. But in reality, that's right. The breeze bed is, changing. Even the shape, everything is changing. So for the moment, we don't have the capability. But that is our developed goal for the future. We have to add this simulation capability with changing the breeze bed.
But this is the limitation for the COCO. Is the COCO limitation?
Yeah, that is a limitation for the COCOMO, but I think we have the source code. It's able to make some change there, but for the moment, it's not the task for Yang Li because she's going to graduate for this year. So, but probably for another PhD student.
These
also,
are new
we
ideas.
have this idea have the surrogate model because there maybe it's more easier to implement this dynamic change of the breeze bed. That is possible, I think.
That'll be very interesting to see when. Yeah. Thank you.
Okay, thanks. So I'm going to talk about the MISTI experiment oxidation of the chromium and iron mixture in water, and also salinity effect on steam exposure. So this basically, let me change my point. So this basically done by our two PhD students. One is Chang Gu and I is Yu Chen Deng. I'm going to make this sentences presentation on behalf of them. So here is what I'm going to talk about. First is why we want to do this work. Yeah. So the second is what is MISTI and what is the approach of the MISTI. Then I'm going to present briefly three pieces of work. First is this the chromium iron oxidation experiment. There's experiment of the salinity effect on steam explosion, and finally is the salinity effect on film bonding. And I come to summary and outlook. So yesterday I already mentioned for the quorum risk, we have two issues in our Swedish reactor context. First is the base coolability. We want to do the research, try to demonstrate how the breeze bed is coolable, at least for the boiling water reactor, right? Of course, we can also use the knowledge for the pressurized water reactor. So, and then another issue is the steam explosion, because when we flood the water, we have to face this problem. We may have the steam explosion. So here is the picture how the steam explosion will happen. First, you have the jet fragmented in the water pool. Then you form a premixing the droplet with water. Then you have triggering at some place. Then you have propagation, and finally come to the explosion phase. So the study of steam explosion, you may know there's already a lot of experiments included Faro, oil, and Klutos. They are large-scale experiments, so they are more like integral tests. Of course, we also have this default test. We can also consider that as kind of a field coolant interaction study. But there we are more focused on the breeze bed formation. So in the MISTI approach, at KTH, we are more looking at the physical mechanism. Yesterday, I already mentioned, we want to look at the limiting mechanism for steam explosion and energetics. So here is some effect we want to investigate. For example, the mild solidification, also void. When you have the film boiling, or you have the non-condensable gas, then this will affect the steam explosion energetic. Also, we know the material will affect the steam explosion. So there's already a lot of study previously. But the start from APRI 10, we try to look at the oxidization effect, because we know in the column, especially for the boiling water reactor, we have a lot of metallic melt, right? So one of the two components is the zirconium and also iron. So if we look at the zirconium at the high temperature, we may have such a reaction. So basically, if you have such a reaction with water, then you're going to release the non-condensable gas hydrogen. Also, you'll release the heat. So both will affect the fuel coolant interaction or steam explosion. So that's very important to study this effect. Of course, when you set down the floor of the cavity, if you continue to have this oxidization, this will also affect the coolability. So another study is the seawater effect on the fuel coolant interaction. Yesterday, we already heard about the Fukushima accident from Chalmers' work. They also do some effect of seawater on the iodine chemistry or the fission product, behavior. So the seawater for us is very natural. We are wondering if we inject seawater to the reactor, what is the effect on the steam explosion or fuel coolant interaction? So basically, this becomes our motivation for this study. So what is the MISTI approach? MISTI basically is a micro interaction in steam explosion energetics. So our idea is we want to try to create a very well-controlled condition and a well instrumentation, so we can identify the key physics in the steam explosion. That's the idea, to compare the large-scale experiment here, where you have everything is mixed together, so it's difficult to identify the mechanism. So this story is from Roberta, actually, when she did her PhD study. So what we do is we just look at only one single drop. Then we prepare the droplet in the furnace. We melt it. Then we deliver it into the water pool. Then we have instrumentation try to look at the evolution of the droplet on the explosion. So that is the idea. So here is how it looks like. Again, this from the shaft system called simultaneous high-speed acquisition, X-ray radiography, and photography. The idea is when you have the explosion, if you only use the regular, photography, you only can see the bubble, you cannot see through. So what we have is we add X-ray, so we can see both bubble dynamic and also the droplet dynamic. So you can see the white one is the bubble dynamic. Then we have also droplet dynamic. So this is a unique part for this facility. And here is some more studies so far we have been done. I already say we are focused on different material. You see we start from low melting temperature and low melting point material like the SN and ZN. This melting temperature is from 2030 degrees to 420 degrees. Then we start using kind of similar material, oxidic thorium. Until last phase APRI, we start to upgrade the facility. The idea is we want to move to the high temperature operation of the facility. And finally, if we want to operate the facility with maybe the prototypical material. So in last APRI, we didn't operate with the high temperature melt like the aluminum or also zirconium. We did a field test with the zirconium melt. So on this facility, so far we already graduated the 2 PhD students. One is Roberta, sitting here. Also have another student graduated in 2000, I think it's 18. Luis. So here is the activity in APRI 10. Firstly, we try to upgrade the facility, MISTI facility, to operate with the zirconium and iron mixture. So first is how to prepare the mixture. It's also kind of challenging work. So we did a lot of study how to prepare the mixture, and also develop a kind of compatible furnace which can melt this mixture. Also develop kind of measurement system of hydrogen production, because in the last phase of APRI, we use the image processing to calculate the hydrogen production, but we found because sometimes the bubble is not irregular. Also, maybe you may have the steam in the bubble, so it's you may have some error. Also, we did the hydrogen production from SEM analysis of particle. Also, it seems the error is also high. So finally, we want to develop kind of a system to measure the hydrogen production. Then we use this system to investigate quenching phenomena of this mixture in the water. Then we also did some tests for the single droplet steam explosions in water. Also change the salinity, not only seawater. So see if how the salinity will affect the steam exposure. And because we know the steam exposure is closely connected to the vapor film stability, but in the single droplet steam exposure, the droplets is moving, it's difficult to observe the vapor film behavior. So we instead to do this experiment, we use a kind of fixed wall quench experiment, so we can have more close observation on the vapor film instability. That's why we do this hot particle quenching in seawater. So regarding the test metric for this zirconium iron mixture, so here is the composition we select based on this phase diagram. You can see we have more coverage of the composition compared with prototypical scenario. But I think that is try to have more data, coverage or database. So here is how we are going to do the experiment. And for the preparation of the zirconium and iron mixture, we have 3 approach. We start with the mix, order the powder of the zirconium and iron and mix, try to make the tablet. But we found it's difficult because it's very easy oxidized during the preparation. And that's why the droplet will stuck, or the melt will stuck in the crucible. The second approach is to order the pellets of this two material. Then we cut pieces into the furnace, try to melt and mix them. But we found it's difficult to have well mixing. Also, it is stuck in the crucible. So finally, we contact a company. So ask them to make this alloy for us. They have special furnace, so it's easier for them to make it. So we call it customized ZR alloy. So we found this will be much, at least the composition is more uniform and also easy to deliver droplet. Then for the furnace, we come up with this idea of this dual crucible or double crucible. We are heating the out crucible. That is in the crucible, which will be compatible with the new material. So we tested for the inner crucible. We tested different material here. I listed here, and finally we found that this one MgO is the best within this 4 candidates. It's so we finally come up with this design of the furnace. And another development in the hydrogen collecting system. Here we have this. I already mentioned. You can see the bubble is sometimes not regular, so it's difficult to use the image processing. So we try to develop this such a system. Because this is the bubble rising, and then we collect it into this cylinder. So that's the idea. So after this, all this kind of modification, here is the facility system. You know, here how it looks like. We have this hydrogen collecting system, and also the double crucible in the VSP facility. And here is the test production so far. If you look at the table, unfortunately, we still have a lot of failure in the delivery of the droplet. So you can see only maybe half of them were successfully delivered. It's still a challenge. For example, melt was stuck in the furnace, and also sometimes the melt just fell without formation of the droplet, or before we form a droplet. Or sometimes you have leakage in the argon gas supply, so we have some oxidation. So it's still it's challenging. It's difficult material to work with. This the chromium and the iron mixture. So we will try to improve. Let's see. I will show some preliminary result. Here's some video. Go back to. So this the first one is the zirconium droplet, the pure material. The second is the mixture. So maybe show it again. Okay. So here is basically the very direct observation. Is it seems the oxidation of the pure zirconium is much intensive than the mixture, right? If you look at the picture, you see here is much brighter in this zirconium oxidation compared to the mixture. So also, if you look at the hydrogen production, we can see this can form this. You can see if we use the pure material. This is a repeating test. So you can say, oh, it's almost, it's more than double of the hydrogen generation for the pure zirconium oxidation experiment. And other observations, I think, first is so far we don't see any steam explosion. I think most probably due to the generation of non-condensable gas. And also the droplet or debris stay at high temperature or longer period compared with the oxidic droplet due to a release oxidation heat. And also the morphology of this zirconium iron mixture debris particle is different from the oxidic material. But as you already see, we just have a limited test, successful test one. So I think this is just preliminary observation. So we will come up more idea about this maybe later. So the second piece of work is on the salinity effect on the steam explosion. So in order to do this, we use similar to material tin. It's the melting temperature, melting point much low, so it's easy to operate. Then the coolant temperature is 22 degrees, and then we use the deionized water, we call it DI water. So then we also have the seawater. This salinity is around 35%. Then we have also diluted the seawater. The salinity is half of the seawater. And we perform the melt at the temperature 600 and 800 degrees respectively. So in order to look at the difference or the effect of the salinity of the steam explosion, we have two definitions in this study. First is the frequency of the spontaneous steam explosion. This basically is the number of a test which will have the steam explosion. That divided by the total number of the test under the same condition. We call it the frequency of steam. Then the depth of the spontaneous steam explosion. That is the distance from the surface of the water pool where the steam explosion will take place. So basically, it's also the measure of the depth the steam explosion will occur, or the timing. For example, if the distance smallness means steam explosion will occur earlier, right? So here is this two parameter, how this salinity will affect these two parameters. First is the salinity effect of the frequency of steam explosion. Then we can see for the 600 degree melt temperature, you can see the steam explosion frequency is increasing with the increasing salinity, right? But the interesting is if we further increase the superheat of the melt or the melt temperature, the influence seems decreasing. That is, and then if you look at the depth of the steam explosion, you can see also the steam explosion will occur near the water surface if you increase the salinity. This means, right? And or you can see if you have seawater, the steam explosion will be more easy to occur, yeah, because the traveling distance will be less. So, of course, if you look at the temperature effect, when you have the high temperature, for example, melt temperature, it seems the salinity effect is decreasing also. So it seems there's a temperature range for the melt where you can have more effect of the salinity. Here is a more numerical effect of this salinity effect corresponding to these two pictures. So I will not go to the detail. The second, the last piece of work is about the effect of salinity of film bonding or on the vapor film instability. So here the idea is we are going to hit the sphere in the induction furnace to the high temperature, for example, 100 degrees. Then we insert this ball into the water pool. Then we also have thermocouple in the middle of the ball. The idea is look at the film instability, also the quenching behavior. So here is how it looks like. This picture sequence shows the quenching process. You can see you start the form of the film and finally come to the stable film bonding in the water pool. And at some maybe 10 seconds, you start to have the quenching. This means the film will lose the instability and then the surface will be wetted. So basically this temperature, we call it the minimum, the temperature for minimum film bonding, or we also call it the Lent frost temperature in the boiling curve, right? So if you look at this this curve or temperature history for the sphere, you can see in the seawater the quenching point is earlier. First, it's earlier. Also, the temperature or the temperature of minimum film bonding is higher than the DI water at the same temperature. If you look at it, this figure shows the Biot number at different time, and we can see before the quenching, the Biot number is less than 0.1. This means we can use the uniform temperature assumption to estimate the heat transfer in the sphere. So here is more data on also the coolant temperature effect. We have both DI water and the seawater. For the A star, B star, C star is the DI water. This means without any salinity, right? So basically, you can see if the water temperature is decreasing or the subcooling is increasing, then the quenching will start earlier. Also, the Lent frost temperature or the quenching temperature is higher. So same for the seawater. Seawater is the dashed line A, B, C. Interesting, you can see this decreasing, or also the quenching changes much significant compared to the DI water. So and at the extreme condition for the 35 degree of the seawater, you can see we actually don't have any establishment of the film boiling. This means it's, quench temperature is almost same as the initial temperature. So it's interesting. Also here we show this heat flux of the sphere surface. And from previous slides, we already see the coolant temperature will affect the quenching temperature or length frost temperature. So here we can see it's almost linear, decreasing with the coolant temperature increasing, right? And this is the DI water, right, points. And this is the seawater. Basically, this guy gave us the idea how the seawater will affect the quenching temperature or length frost temperature. And also, then we can observe this correlation between this coolant temperature and also the minimal heat flux, temperature for film boiling. So also there's comparison between different study here. So here come to my summary. Basically, the MISTI facility was further upgraded to perform experiment with the zirconium and iron mixture. And the preliminary results show that this mixture alloy react with coolant less intensive than the pure, zirconium during the droplet quenching process, leading less hydrogen generation. And no steam explosion was observed in both, pure zirconium and the zirconium iron mixture test due to the suppression of non-condensed gas. And the spontaneous steam explosion is prone to occur in seawater, and the tendency is more pronounced with increasing salinity. The quenching process of a high temperature particle is accelerated in seawater due to the elevated length frost temperature. So also the salinity of film boiling surrounding particle decrease with the increased salinity. So we may speculate in the real accident scenario when we have the metallic melt in the core. The steam explosion risk should be decreased. So here is outlook. We are going to continue upgrading of the MISTI facility. So first try to increase the efficiency of producing the droplet. And the second is improve the visual quality of the bubble and droplet. And most probably we are going to introduce the X-ray image again, because I already mentioned in the shop system we're supposed to have X-ray also, but so far we didn't use that. And you can see the image is quite, bright. We cannot see so much or see through the image. And the third point, try to also reduce the measurement error, for example, the droplet temperature. And also the facility will be employed to perform a more systematic study on the quenching phenomena of this metallic melt in terms of effect of this composition and water subcooling and wet melt superheat. Finally, we want to try to go to the mixture of this with the oxidic in this mixture. That's all. That's all from me. Thank you for your attention.
Thank you, Wei Ming. I have written some questions and some suggestions already in the comments. Maybe we're not going to be able to go through all of them. But if we look at the seawater, you say that it promotes spontaneous steam explosion because it has a less stable film boiling. How does the faster quenching would affect the energetics, because you have a less stable film boiling might change the droplet fragmentation, and that will reflect on the energetics. And that's what we saw in the nanofluid experiments, that we saw a delay, but then when they had a steam explosion, it was very energetic. It was the other way around as the seawater. So very interesting to know how the energetics of a single droplet steam explosion changes with seawater. We know it happens before when it's spontaneous, but if you have a triggered one, how would that? What would you expect how would you expect to happen?
Yeah, right.
In terms of energetics.
That's good comment. Yeah, because for the moment, when you look at this very spatial condition, but you're right. It's when we look at the whole picture, yeah, it will first affect the jet fragmentation. They also affect the droplet size. They come to the triggering or their propagation. So, yeah, that's something we have to consider. Yeah.
That'd be interesting to see, because it's the vapor film gives you one side of the story, but it would be nice to know how does it affect the energetics, which is connected to fragmentation. One point that I would be interesting to see is to find a mechanism. How does that work with, for example, borated water? Because it will be likely that in a PWR you're going to have water with bore inside. So how would the borated water affect on the steam explosion, or vapor film instability, or stratified steam explosion?
Actually, we had some study about that, but we never presented because we still, yeah, if you have some floating objects or something, you talk about that. Is that?
No, I was thinking about the borated water that you add, especially in the PWR, so you can control reactivity. So you have bore inside the water. So I wonder how would that affect steam explosion?
Yeah, that's right. That's we actually already have some bore. We did some tests with some bore in the water, but the findings cannot conclusive yet. Yeah. That's why we did present so far.
Yeah, so I guess we are running out of time. I wrote some suggestions and some questions. You, Cheng Bing, answer some of them, but it'd be nice if you could just check on the chat window later on. Thank you, Amy, very much.
Okay. Okay, thank you. Bye.
Thank you. Now we're going to hear from, we leave steam explosion and we go back to avoiding a vessel failure after all. Walter Villanova is going to present us the experimental numerical studies on the spray of reactor pressure vessel external surface. The floor is yours, Walter.
Can you hear me now?
I do hear you and I can see your presentation.
Okay, but not yet. Okay. So I can extend a little bit, right? So it was 2 minutes.
Go ahead. Just go for it. We're just losing lunch time.
Okay, so this talk will be about the experimental and numerical investigation of cooling the external surface of a reactor pressure vessel by water sprays. Okay, a brief outline. First, the introduction, and second, I'm going to present the spray cooling facility called SPAYCORE. And then first, I'm going to present first results will be about the Cantal. This is the iron chromium aluminum sample. Cantal is relatively cheap and abundant compared to carbon steel, so we can actually do a lot of tests with Cantal. And this is going to be followed by complementary numerical simulations to be able to determine the heat transfer coefficients and also the maximum heat flux that we can obtain, that we cannot actually attain in the current facility. And experimental results for carbon steel SA302B will be presented as well. This is not this is quite common material used in reactor pressure vessels. And then to end, I'm going to give some conclusions and a brief outlook. Spray cooling. Okay, as you know, there are many things that can get hot, like the transistors or the processors in your computers, your engines in your car. More extreme, the space exploration systems, turbine blades, and all those things. In nuclear engineering applications, of course, the core can get hot. That's why you have coolants. And during a severe accident, extreme case, the core, of course, can melt down and then can relocate to the lower head. And this corium can impose a heat load on the vessel wall. So if you don't hit if you don't cool the corium on top or outside of the vessel, then most likely the vessel will fail. But as already Roberta mentioned, in the SUMGIS of Swedish light water reactors, we don't have IVR, ERVC. That means that we don't externally cool the vessel, whether by flooding or by spray. So this is not included in any SUMGIS in Swedish light water reactors. So this is more like an innovative attempt to investigate the spray cooling of the external surface of the RPV. So there are many ways to cool a surface. As you can see the plot on the left, we can cool it by air, by water, and we can do it by single phase or even by free convection or forced convection. And then we can have a phase change. We can have a single phase or two phase. And the heat flux, of course, increases as you go from, let's say, from air to water or from single phase to two phase. As you can see here, the water boiling convection only reaches about 1 megawatts per square meter. But for water spray cooling, you can actually reach the order of 10 megawatts per square meter. And the corresponding heat transfer coefficients that you can attain with water spray cooling is about 200,000 to 400,000 watts per meter square Kelvin. So let's take a note on these numbers because it will be used later on. Looking at the reactor pressure vessel, so the idea is to use water sprays externally to cool this hot surface. Of course, the study is not about optimization of this arrangement of this sprays, but basically if we can obtain high heat fluxes that is relevant for higher power reactors that can reach as high as 2 megawatts per square meter. Okay, so looking at these examples of nozzles, this is a schematic on the bottom of the figure. And also some arrangement of 6 nozzle sprays that we used during the experiment. And this is the schematic of the sprays. So basically, if you have droplets coming out of the nozzle, then it will impact the hot surface, and then it will have a heat exchange with the hot surface, and it cools this surface, and then it impinges, and then it pushes to the side. So there are many of these, of course, droplets that can interact with other droplets and also interact with the film that can be formed. It can even, let's say, if you have in the cases where you have a water vapor film that will form in this, it can impact that. It can actually make it unstable. So in comparison, for example, for pool boiling, if you don't have such, then it's just a forced convection. Then it comes early, this latent frost effect. But for spray cooling, this water droplets impact on the surface, kind of like have a significant influence in the formation of a water vapor film. But as you can see here, this is only for a single spray. What happens on the side is that you don't have this. When you don't have this water spray, so it's just similar to kind of like pool boiling. And also the schematic doesn't also show the interaction of the nozzles, the sprays, for example. So what you can see later on is the interaction of these sprays when it comes to the heat fluxes and the temperature profiles on the hot surface. Now, why are we pushing this? There are some advantages of spray cooling for severe accident applications. For example, for in-vessel retention. One, of course, which is obvious, which is that we can have high heat fluxes. We can reach 10 megawatts per square meter in principle. Second, there's no need to create a water pool in the cavity specific to vessel retention flooding. It takes a long time to flood, of course, the cavity, especially if you're thinking about the Swedish BWRs. It takes about more than 7 to 8 hours just to flood the. So while the time scale for vessel failure, for example, is in the order of 3 to 4 hours, for example, from the start to the scram. Third is that it also requires less water inventory, so you can use much less water compared to, let's say, filling up a full the whole cavity. And lastly is you can have fast activation, so you can compare to water filling. Okay, this is the spray core facility. This is the picture on the left. You can see the full setup. You can see in the middle, this is the compartment. And then you can see the infrared camera pointing towards the top surface. The top surface of this compartment, you can see in the top view here. Maybe I can use just a second. Okay, you can see the top view here, which is painted by black due to it's much better for infrared measurements. And there's a thermocouple that you can see to set the emissivity of this surface. So you can see this inside of this compartment, you have the nozzles, and then you can see here the wetted surface, or the surface that is hot, that will be cooled by the sprays at the bottom here. And you have also steam venting here, which is you can see there, and then the infrared, like I said, and this is you have electrodes here. Now what I can do is I want to show the instant of this spray. You can see the six nozzles here. You see how they interact, the points where they kind of impinge the surface. This is, by the way, it's a cold transparent glass, just to see this dynamics, this kinetics of the spray. And then you can see how they form this pattern. And correspondingly, if you use a heated sample, this is the infrared that you can see from the top, okay, by this water sprays. We use some of the key features of this facility is that we can rotate it from 0 degrees. Now this is rotated about some angle, as you can see here. So we can rotate again, and let me choose we can rotate it in this direction, so also the infrared can follow, and also. So from 0 to 90, as kind of like with applications to an RPV, where you actually need to cool the RPV from 0 to 90 degrees in polar angle. And the other feature is that we use a 12 by 8 centimeter sample. This is actually very large, relatively large compared to typical experiments in spray cooling. In typical spray cooling experiments, they use a very small, like 1 centimeter by 1 centimeter, and only use a single nozzle. And this is also one reason why you can easily reach high heat fluxes in the order of 10 megawatts per square meter, because you're only considering, for example, the impingement, direct impingement region, for example. Okay, now we look at the one of the first results. This is let me just again. Play. So this is the effect of the inclination. As I said, we can rotate the facility. We can look at the 0 degree inclination. These are the 6 sprays. Again, this is the pattern, and there's a thermocouple that you can see there. This is for the 0 degrees inclination angle. It's a little bit lagging, but you can see that the change of this pattern of this infrared camera, which shows the temperature. And also for 45 degrees, you can see similar patterns, but there's you can see this slight change in this region, in this part, in the lower part of this infrared profile. And for 90 degrees, Yeah, you can see also this kind of this is the liquid drainage, basically, because this is rotating 90 degrees. So basically, this is the lower part of the sample, and then you're spraying this hot surface on this, and then you have the interaction region, you have the direct impingement region, and then the water can drain down the sample. As you can see here, the dynamics in the spray interaction region and the side corners are entirely different from the central region of the spray. You have stagnation regions, stagnation areas that can be found at high temperature regions. This will actually set the lower maximum heat flux margins compared to that in the central spray area. So you have different heat flux profiles. For different inclinations, we can find we measured the delta T. This is the delta T from from this thermocouple that you see here, and there's a corresponding thermocouple at the back of the wet area, wetted or sprayed area, and we can measure the delta T at different inclination angles. You can see that we can reach up to 21 degrees Celsius for different powers or different steady heat fluxes. Now, the influence of input power. This is done for different for 0.5 megawatts up to 3.1 megawatts per square meter. You see that an increase in input power significantly increases the maximum temperature. You can see from 59.5, 80.4 up to 144.8. This is on the dry side. Okay, we don't have access to the temperature profile on the wet side because, as you can imagine, we can only put the thermocouple there, and we cannot have any other even especially infrared or other instrumentation. But so the maximum temperature in the dry is specifically on the interaction zones. Here, as you can see, the change in the color from this case to the high heat flux case, which can get to 144.8. But the temperature on the direct impingement, you can see that it's not much drastic change compared to the maximum temperature in the interaction regions or interaction zones. Now, we did complementary simulations using COMSOL because in the experiment we can only, there's a limitation in the heat flux, maximum heat flux that we can reach. We need to efficiently cool the sides because it kind of like fail on the sides, on the edges of this sample. So we thought of using numerical simulations to be able to access or to be able to determine this first, of course, the heat transfer coefficients on the spray side, and then use that quantities to determine the corresponding maximum heat flux. So here you see the schematic. It's 80 by 120, and the thickness of the sample and some numerical details. I'm not going to go through now. We use a coupled modules of heat transfer in solids and also electric currents using COMSOL multiphysics. And it only takes about 40 minutes on a regular desktop. Now, this is something important that we do in the numerical simulation. We have to make assumptions on the heat transfer coefficients. As you can see, this is the infrared camera on the side, on the right side. There are 6 of these sprays, and we make an assumption that in each of this sprayed surface, we have 3 different sub-regions or sub-areas. First is the direct impingement region, which is shown by this square. So we may, and then the next one is the outer area or the water film regions, and then the edge or intersection regions. And in each of these regions, we have corresponding like maximum heat transfer coefficients. It's H1, and then this is just set up to make the change smoothly or like continuously from one area to the other. Okay. Now, if we look at the numerical simulation results and compare them to experiment, we have cases from 0.5, 1, and all this 1, 2, 3, 4, 5, 6 cases. We show here 2 cases only for 2.5 and 3.1. The one on the left, we see the experiment. And the one on the right, we see the corresponding numerical simulation. As expected, of course, the cooling pattern in the simulation is symmetric compared to the experiment. And then you can see that the maximum temperature, this is 123 degrees, and this is the corresponding 122. Actually, this is we adjust the heat transfer coefficients such that the maximum temperature matches. Okay, so in all of these cases, we do the same process that try to get the heat transfer corresponding heat transfer coefficient such that this maximum temperature, this is only the quantity that we need to match. But as you know, the simulation, you can have access to all the other quantities, even the current distribution, the heat, the temperature. On the wet side, you have access to the minimum temperature, the delta T. So you have a lot of quantities that you can get from the simulation, and also. You can, so looking at the one on the right, we can now plot the different H1, H2, H3. These are the corresponding heat transfer coefficients for different regions. And then we fit this. We do cubic function fitting here for different, for H1, H2, and H3. And then we found that from this fitting, we can reach a maximum heat transfer coefficient, which is located in the direct impingement region, which is in the range of 90,000 to 150,000 watts per meter square Kelvin. Now, as I said in the beginning, this is comparable to the data, which is in the range of 200,000 to 400,000 watts per meter square Kelvin. And also, the delta T, you can see here also the delta T that no, I can show it in the next slide. You can see that there's an intersection here at 4.5. That would be interesting to check later on. So for 3.1, say same case, the 144.8 and 142 here. Now, if we in the numerical simulations, we can given the heat transfer coefficients, we can push or we can get results even for higher input voltage, basically for higher heat fluxes. So this is the case for the numerical simulations only, and comparing getting results for 3.5, 4, 4.2, and 4.4. So like we keep increasing this input voltage or to reach higher heat fluxes, and we see here on the spray side and the dry side. So on the dry side we see 165, and we see in the sprayed side or the wet side we see 145, and also the Tmin and the Tmax. So this is comparable to what I've shown before about the 20 degrees delta T that was measured during the experiment. So as you can see, that the behavior of the increase of the temperature here, and also the change in where the maximum temperature is located is on the dry side. See here in the one on the interaction region. But when you increase this actually you see the maximum temperature located at the water film region. When Q is set at 4.5, the sample fails because the highest temperature on the dry surface exceeds the melting point of this alloy, Cantal, at about 1500 C. So the maximum heat flux that is expected to occur is between 4.4 to 4.5 megawatts per square meter. Now, we go back and now I show you the experiments that was done on a carbon steel, SA302B. This is common in commonly used in RPVs. And this is this experiment consists of steps of 5. Well, this 5, 10, 15, 20, and then 23. Actually, this is we have to like gradually increase these things, and then stop and then see if it's stable. So this is the case for 0 degrees and for 90 degrees angle of inclination. As expected, the escalation of the temperature intensifies as the input power is increased, but the cooling pattern is maintained to some degree. You can see that it's although the temperature is kind of escalates, and you can also see here the liquid runoff again due to gravity, comparing the, for example, the 0 and the 90 degrees. This is the direction of the gravity here at 90. Okay, the influence of water flow rate. We increased the water flow rate from 8 liters per minute to 15 liters per minute. That corresponds to about 2.5 liters per minute per nozzle. As of course, as expected, again, higher water flow rates reduces the areas of the hot regions. These are the red patches. But the maximum temperature is relatively maintained within 143.5 to 145.4. You can see the maximum temperatures on the upper left corners of each of these infrared profiles. The higher flow rates have higher momentum to push the liquid outwardly. Thereby, it reduces these areas of this interaction between sprays. As you can see, the increase of these areas, these green areas, in as you go in higher flow rates. The maximum steady heat flux. So we tested this for the 90 degrees inclination angle. Okay, the one reason, of course, is that it is also where you can expect the highest heat flux. If you're familiar with the focusing effect, for example, for a 2-layer configuration, you have the much higher heat fluxes in this area, which is around this 90 degrees inclination angle. So we tested, we increased the input power from 25, 27 to 29 kilowatts. Now you can see the increase in the maximum temperature from 146 to 149, and also the patterns is kind of similar as well. But in this case, even as we increase this one, we have failures on the edges of this sample. This is the reason is that we need to efficiently cool the sides of this sample. The corresponding steady heat flux for this 29 is about 3 megawatts per square meter. Now, to conclude, we have demonstrated the feasibility of spray cooling as a possible in-vessel melt retention strategy for high-power reactors, which can reach up to 2 megawatts per square meter for more than 1,000 megawatt electric NPP. We obtained steady heat fluxes up to 3.1 megawatts per square meter for the Cantal heater, for the Cantal sample, up to 3.0 megawatts per square meter for the carbon steel. This is much higher than the expected maximum heat flux that can be attained with pool boiling, only around 1 megawatts per square meter. There were some influential factors affecting the steady heat fluxes, such as the inclination angle of the spray with respect to the vertical axis, and also the input power and the water flow rate that have been investigated and shown. And finally, we performed complementary numerical simulations that generated the heat transfer coefficients, which in turn are used to predict the maximum heat flux that can be attained for the given system. As an outlook, the improvement of the side cooling of the samples in order to reach even higher heat fluxes and possibly confirm the maximum heat flux prediction from the numerical simulations is one of the high priorities. Although for severe accident application with in-vessel retention, there's actually no need to obtain heat fluxes higher than 3 megawatts per square meter. There are several other influential parameters that can also be investigated, which were not done during this experimental campaign. One of them is the surface roughness. Another is the nozzle to surface distance, and also the water subcooling. Although water subcooling, sometimes like we do the test during the summer or during the winter, we see a little bit of difference. But we didn't systematically investigate this. And also the pitch to diameter ratio and also the nozzles arrangement. I think we need to optimize the nozzle arrangement such that we can minimize these interaction regions. Next is that the carbon steel SA533B1, which is common in American as well as Swedish light water reactors, has yet to be tested. And in terms of modeling and simulation, we need to improve the by the simulation of the jet sprays and its interaction with the heated plate. And in this case, then you don't have to guess the heat transfer coefficient, or you don't have to like set it. You can obtain it from the heat transfer between the drop and the hot surface. And finally, there are also other possible applications of spray cooling that can be considered. One of them is spray cooling of the debris bed in the cavity. Another is X-vessel melt arrest by sprays, and also spray cooling bottom of X-vessel melt catchers. That's all. Thank you for the sponsors, and also thank you for your attention.
Thank you, Walter. Well, you didn't take that long.
I'm giving time for questions.
Yes. I have a question. It's going to come to a time that you might be able to develop a better numerical simulation. Like you said, you don't have to guess the heat transfer, for example, because maybe it'll be easier to test like all the parameters you were talking about, like surface roughness and the pitch. It will be a nightmare to do that experimentally. So what kind of tool you were thinking about?
Well, CFD, of course, for this sprays. Now it's like COMSOL, it doesn't have this yet, this capability. So it's a lot of work actually, just to model the sprays. I've seen some papers on this, or some works. They use also different tools like Fluent, or they test different. But to be able to couple all these things together, you know, the sprays, the joule heating. So you're coupling many different physical phenomena. So which makes it more challenging. But if you just simulate the sprays, then.
Let's talk about droplets here, surface roughness. So I was just wondering, that itself would be quite a challenge. Interesting,
and the
but quite a
surface
challenge.
roughness, yeah, the resolution of the surface roughness is another challenge. Because it changes the wettability, it changes the even if you use like hydrophobic or hydrophilic, and then with the surface roughness, so it's yeah. A lot of
Although I don't think you can change the reactor vessel roughness. You can test them though.
Oh yeah, speaking of that, this is, as you see, this is a raw material, like a fresh material. You know, it's a different picture if you look at the external vessel. Entirely different. So,
yeah.
You know, surface roughness for sure. There is surface roughness there. So yeah, it's more complicated in reality if you want to like apply it. So, and it changes.
The next step to look at the simulations, or to do some more experiments to refine them.
Well, you can do this, I guess, in both. Like what you can do in the experiments, for example, that can be easily done to get some insights, to just see the effect. For example, there you can, for example, play with the some kind of like engineered surfaces, but in the numerical simulations
also, maybe if it's a database for validating your simulations.
Yeah, also it provides a database, of course, but it gives. So that's why we always call this like complementary. That each of which each of these approaches, you get something.
Last question from my side. Let me just see if somebody else. I have the tendency of taking over. No, here.
There's also lunchtime.
Yeah.
To talk.
It's about the 2-3 megawatts per square meter. That's what all you need for the investor retention. There was much discussion about that, and it comes also from the CRGT cooling time, the research on that. So what you're saying is that if for 1,000 megawatts electrical, about a reactor, you will not need more cooling than 2 megawatts per square meter, 2-3 megawatts per square meter to be able to get an EVR.
Yeah. Well, the thing is that it's the thickness of the vessel as well. I mean, like, for example, just to give you an example, with a 2 megawatts per square meter, the thickness of the vessel is about 16 millimeters. And the temperature on the left, on the hot side, it will be about 1173 K, about that. And then with the cooling, of course, let's say you put like a coolant temperature on the other side. So you're looking at this thickness, it's very, very small already, 2 megawatts per square. So just imagine if it's higher than 3, then it's already, you're looking at the very thin. It's probably like it's gonna fail already. It cannot hold the weight of the corium, and also the internal pressure. So it's already very. So it's probably is a limit that you can even set for such applications.
That would be nice to have some engineering, like a little bit of a extra, just in case. But anyhow, thank you very much, Walter. It was very comprehensive presentation and very interesting topic.
Thank you.
Well, I think it is now time for lunch. Henrik, you tell if it's lunch will be between 12 and 1, and I will see you back around 1, if I'm not mistaken. That's it, right? I just lost it a bit here. Yes, lunch between 12 to 1, and I see you back at 1. Thank you very much for all the presentations.
Welcome everybody to session number 5, which is dedicated to international projects. We will have 2 presentations in session 5, and I will be the moderator. My name is Patrick Isaacson, and I work at SSM with Civil Accident Research Coordination. I am also part of the APRI steering group, and I will be the chairman of APRI 11. Before I introduce our first speaker in session 5, I would like to say a couple of words about international research platforms in order to provide some context for you who are not familiar with these platforms. SSM and KHH are typically involved in either EU projects or OECD projects. In EU projects, the research initiatives typically comes from the EU Commission together with some financial support. The funding is distributed among the involved partners depending on the amount of work which these partners do in the project. And most of the partners also contribute with their own fundings to the project. In EU projects, there is also a representative from the EU Commission which supervise and overlook the project. In OECD projects, the initiative typically comes from one or several research organizations in a member state of OECD, and OECD itself acts as an administrative and supporting organization. The actual research that is being done is provided by a dedicated partner called operating agent. And the partners in the project which are participating in the project except for the operating agent also contribute to the project. The country that the member state that hosts the operating agent typically contributes with the majority of the funding, up to 50%. And the rest of the funding is distributed among the participating partners according to the GAP of the different countries, which in case of Sweden means that we typically contribute with 1.5% of the total budget cost for the project. With this, I hope it will be a little easier to follow the discussions and the presentations that will be in session 5. Now I would like to introduce Professor Sebastian Besta, who is head of Nuclear Power Safety Division at KTH. Sebastian is an expert in physical chemistry and material science, and he has a solid and impressive background in Korean research, and he has been leading several big-scale experiments in the OECD framework with corium before coming to KTH. And Sebastian will present an overview of the international research activities in severe accident in which KTH and SSM are involved. So please, Sebastian, go ahead.
Thank you, Patrick. I will now try to share my screen. Do you see my slides?
Yes, I do.
Excellent. Good afternoon, everyone. I will present you recent progress in international projects on severe accident research and Fukushima Daiichi nuclear plant decommissioning. Let me introduce my co-authors. They are Patrick Isaacson from SSM, who is chairing this session, Wei Min, Walter, Andre, and Alexander from KTH NPS. They probably are also attending this session. I will start from Fukushima-related projects at OECD NEA. Then I will speak about several research projects with a wider research and technical context. Then I will give you a few ideas about IEA coordinated research project on investment retention. Show you a few slides about follow-up research for safest and IVMR EU projects. And my last slides will be about recent progress with preparation of Fukushima plant decommissioning. So why it is useful for you to know about this progress? We believe all that the multi-unit accident at Fukushima Daiichi is among the most important sources of knowledge about severe accident progression and phenomena, specifically if we speak about boiling water reactors. Several projects have been partially presented at the previous APRI final seminar, so this presentation can be considered as a continuation. In this presentation, of course, I will have a primary attention to the active research projects and to the research projects where KTH and SSM participate. So more projects can be found at the EU web pages, IEA web pages, and OECD agency MyNEA web page. When we speak about OECD, it would be maybe good to understand that at NEA, the OECD activities are coordinated by two committees. First, the all Fukushima projects, which are more plant-related and safety-related, they are coordinated by the Committee on Safety of Nuclear Installations, while some projects which are closer to fundamental research are coordinated by Nuclear Science Commission. So BSAF, PRIADES, and ARC-F projects are under CSNI, and TICOF project, which I will be speaking about, is under NSC. If you will see on this block scheme, you will see three Fukushima-related projects: BSAF, PRIADES, ARC-F, and it could be good to understand in general that SAREF, BSAF, and post-BSAF projects, they generally provide modeling and calculated plant data from different activities and different benchmarks, while PRIADES project coordinates preparatory work for debris analysis and removal, even reprocessing. And ARC-F project has its main focus to the safety analysis in more general context, and TICOF assists to all these projects with material science knowledge and contributes all projects with material data and thermodynamic properties and evaluations. So I will start from more research project from TICOF, which is thermodynamic characterization of fuel debris and fission product on scenario analysis of severe accident progression of FD and PP. And this project is a kind of application of thermodynamic approach to assess thermochemistry during the accident, but at the same time, this project tried to use data, plant data, and results of these assessments to improve thermodynamic databases, which we use in severe accident analysis. There are two task forces in TICOF. The first one is around corium and fuel, and the second one about fission product behavior. In Corium and Fuel Task Force, there are 6 tasks like identification of priorities, reassessment of thermodynamic functions important for modeling, identification and prioritization of improvements necessary for specific systems and subsystems, updating general knowledge of physical chemistry of corium, physical chemistry of molten corium concrete interaction, and of course thermodynamics related to long-term and very long-term corium behavior. For example, degradation of corium from the material point of view, leaching effects, and possible release of radionuclides into the water during this leaching process. In their task force for the fission products, there are 4 tasks. First one is qualitative thermodynamic evaluation of cesium behavior. Second task is assessment of physical chemistry of complex cesium containing materials and systems, thermodynamic systems. Third task is also around long-term behavior of fission products, and task 4 is about general assessment of thermodynamic data for most important radionuclides. What I also would like to mention, currently we are in the very end of TICOF project. The TICOF final report will be prepared quite soon and probably published during this year. And we are now in the preparation of the TICOF second phase. In the following few slides, I will give you some examples of activities and results obtained in TICOF. We can start, for example, from the task force 1, and the very large part of this task force is benchmarking between different thermodynamic databases. In general, there are 3 databases used in the project, developed in different organizations. Nuclear Mephisto, developed at IRSN, TAF-ID, developed at CEA, and Heracles, developed in PSI. And the quite, I would say, large benchmark exercises were performed between different databases, for example, between Nuclear and TAF-ID, for different corium compositions and for different conditions, reflecting initial core damage, like shown here. Do you see my pointer?
Yes, we do.
Okay, good. Then also corium in the reactor pressure lower head, and finally X-vessel corium. In this table, you can see different composition of corium modeled during these benchmark exercises. Here I would like to show you a comparison between Nuclear and TAF-ID modeling for the C case 1. Composition can be found here. And you can see here that both thermodynamic databases predict quite similar behavior in respect to their amount of phases formed at different temperatures and indicated here. I would say this is a very good example. For other more difficult compositions, different databases can provide quite large discrepancy. What is also a very good part of TICOF both in Task Force 1 and Task Force 2, we were able to organize, and we got very large contribution from the international R&D call. The call was created in 2017 to support experimental studies of high relevance for corium and fission product physical chemistry. So after call was evaluated, the best experiments were selected, and for today we have a lot of new results regarding cesium oxide binary systems from TTH, from Tokyo Institute of Technology, phase equilibria for the main corium system, and for system with boron and carbon from Research Institute of Technology. We have interesting data from high temperature Knudsen fusion mass spectrometry from their Joint Institute of High Temperatures for this system. Delft University of Technology contributed with new data regarding cesium solubility and key phases in barium molybdenum oxygen system. I am now in touching technical Task Force 2 for fission products behavior. St. Petersburg State University provided new results concerning cesium bearing compounds in these three particulate systems. And Khlopkin Radium Institute providing results on leaching of radionuclides, long-term phenomena of leaching of radionuclides from Chernobyl corium and lava. Here you can find some papers where you will find details about new data obtained in TICOF by various organizations. Some direct examples can be found here. Here I would like to show you data in respect to liquid immiscibility for the ternary oxygen zirconium uranium system, and the data are presented as a comparison of their ternary phase diagram, isothermal section calculated at this temperature, with experimental measurements in respect to the composition of metallic and acidic stratified liquids. You see that there is still some space for improvement of both theoretical knowledge and experimentation. Here I have another example of new results in respect to the evaporation of species from this ternary system at very high temperatures. This is reciprocal temperature, and on the top you can have absolute temperature. You can see that temperature is extremely high, and you can see an Arrhenius plot of zirconia relative partial pressure versus reciprocal temperature, published here. Regarding the fission product behavior, you can find some new experimental data measured by Anna Smith in Delft University for this pseudo-binary section of cesium molybdenum oxygen ternary section, ternary phase diagram, and also complementary data to this ternary system, I mean activities of molybdenum oxide and this compound also gives energies in this system with different concentration of the samples. Also papers are mentioned here for possible more detailed reading. What we did in TICOF in Task Force 1, we provided thermodynamic modeling with nuclear database of chorion phase composition in reactor vessel lower head, modeled by Melchor, predicted by Melchor. So we used relocated masses, compositions, and their temperatures in different cells to calculate then in nuclear the phase equilibria is every cell at specific temperature. 3 cases were calculated with different Melchor version, and third case was calculated with activated eutectic model. So there are 3 histories of mass relocation and timing of reactor failure depending from the Melchor code version used in the modeling and depending from the temperature selected as a melting temperature of fuel. And third case, as I told already, was done with activated eutectic model of melting in this code version. And you can see quite different evolution of masses and compositions in the reactor pressure lower head between these 3 cases, but also quite different timing of reactor pressure failure from 9 to 12.3 hours. If we will have a look on the compositions, then you will see that thermodynamic equilibrium, which was calculated at the time of reactor pressure failure predicted by Melchor, at this time, in all cases, Melchor predicts less amount of liquid phase or even no liquid phase compared with nuclear database prediction. So what Melchor show us? It's 100% solid debris bed of this composition. UO2, Zetera, oxides formed from stainless steel elements, and B4C. More detailed modeling with nuclear show us about 78% of solid and about 22% of liquid phase. Of course, this liquid phase is quite important to consider from the point of view of both heat and mass transfer inside the debris bed, but also possibly attacking reactor pressure vessel wall. And if you will have a look on the compositions, solid phase will mostly represent refractory acidic phase, while the liquid phase will be metallic type phase composed of uranium, zirconium, stainless steel, and very small amount of oxygen. Now I am coming to the next project, which is PRIADES, preparatory study of for analysis of fuel debris. Here you have a link to learn more about the projects. Here you can see a list of participating organizations. This project has 3 main tasks. First one on the joint study on fuel debris expected properties and characterization. So we apply our general knowledge about chorion physical chemistry to predict what can happen in Fukushima Daiichi. Task 2, to identify needs and major issues for future fuel debris sampling. And task 3, to plan a future international R&D framework. And important deliverable from this project is recommendations regarding sampling and specific means of analysis from the fuel debris, sampling from the fuel debris, and analysis of these samples. SSM and KTH both contributed in preparation of the report and in the composition of analytical tables for debris cooling functions. These analytical tables give an idea where it would be good to sample corium, what are the main issues for safety which can be assessed from these samples, what can be learned, what kind of analysis can be done, what is the motivation of sampling, and what are expecting benefits. And finally, there are some peered type assessment, how important would be specific sampling in specific location. The next project is ARC-F project, analysis of information from reactor buildings and containment vessel of Fukushima Daiichi. These projects can be considered as a continuation of BSAF and BSAF-2. By the way, if I remember correctly, Patrick can comment maybe, BSAF was organized by a regulatory organization around Fukushima. ARC-F project has 3 tasks. The first one around refinement of analysis for accident scenarios, associated fission product transport dispersion. Task 2 is on compilation and management of data, and task 3 is for discussion of future long-term projects. A lot of organizations from different countries participate in this project under coordination of GAA from Japan. The task 1 of ARC-F has 3 subtasks. I would say this task 1, it's extremely complex and large and involve a lot of different organizations and different activities. So regarding their subtasks, we have a subtask 1A on sensitivity studies for various accident scenarios. Then we have task 1B concentrated around in-depth analysis for specific phenomena, looking in details into their accident progression. And task 1C, quite interesting task for the backward source term analysis and off-site consequence analysis. The idea is we have a strong lack of data of measurements during severe accident at Fukushima reactors, because these reactors of old design are not instrumented by severe accident dedicated measurements. And the idea of this task 1C is to use time-dependent measurements on doses around NPP, and then try to understand in a back way from their these doses dynamics, what was the source term evolution and which scenario can come to this source term. I would say this is very challenging task, but quite interesting, and possibly we can get new knowledge from this task, of course. And so complicated task 1, of course, has a lot of participating organization, and this slide give you an idea about organizations contributing into different groups and different subtasks, and coordinating different groups and subtasks. What were we doing, I mean SSM and KTH in ARC-F? First of all, KTH performed Melkor simulation of Unit 1. At the beginning, we used for that Melkor input developed in VTT by Dr. Sivon, and we simulated Unit 1 with different Melkor versions. Here I show you results of 4 simulations made with different Melkor versions, but also with increased water injection and with and without activated eutectic model. If you will compare, for example, containment pressure predicted in the original publication of VTT and our results, you can see some improvements in our modeling for the time window between 10 and 15 hours. Cases 1 and 2 reproduce the containment pressure better than case 3 and 4. Of course, these inputs are not exactly representing the real inputs of all 3 units. And later on, we, thanks to Sandia National Lab, we got Melkor inputs for units 1 and 2 and 3. And now we can perform more detailed simulation. And we already started with simulation of Unit 3. And I can mention here large deviation between our modeling results and measurements and TEPCO data. Here you can see TEPCO data in yellow and 2 cases of modeling. Case 1 with a leakage area 0.01 meter square, and case 2 with no containment leakage. And still we have quite large deviations, so we need maybe to study in more details the input decks and our modeling. So these results are very preliminary results to be further studied. Now I am coming to the OECD Razao project, which has a larger context. It is for general severe accident research. The project is built for large-scale experimental study of in-vessel underwater melt spreading and in-vessel and ex-vessel debris coalability and MCCI with chemically prototypic corium mixed with real fuel. And in this project, we are going to have parallel analytical activity for model development and for code validation. Here you can find the project web page, organizations, timing, budget, and so on. Here I would like you to show 2 main facilities at Argonne National Lab. Melt spreading experiments will be started in a large-scale experimental facility with thermite generator, preparing and releasing metallic and oxidic melt into the spreading section filled with water. So our colleagues are going to study wet spreading, and this facility will study wet and dry MCCI, also with thermite melt preparation and with a lot of instrumentation in MCCI section. Here I have a photo made in small-scale experiment with pour of prototypic acidic melt into the water, demonstration test at Argonne National Lab. Some conditions for the test are mentioned here. Very fortunate this experiment was not leading to the steam explosion. SSM will contribute in Rosau with supporting experimental study of melt spreading in a shallow water pool with different metallic oxidic and mixed corium simulants. And we are trying now to select the test conditions to reduce steam explosion risk. To give you an idea about consequences of steam explosion risk, I am now activating the second video here. So consequences can be quite severe and will not enable us to understand what is happening during the spreading. So I have 5 minutes, so maybe need to accelerate. Another project is W-Gamma state-of-the-art report on in-vessel melt retention. After a large EU project on IVMR is completed, there are two follow-up projects. One is OECD SOAR project for in-vessel melt retention, and another one is IEA CRP project. So in OECD, we are going to have a focus on material database and its improvement. We are going to provide summary of existing calculations. We are going to develop further methodology of transfer of our results from heat flux distribution and reactor pressure wall ablation up to the RPV integral assessment and safety demonstration. Also, we will work on methodology and best practices for RPV integrity calculations, and we will have overview of large and small scale experimental facilities to understand what is needed in the part of future experiments. More details can be obtained here. Some information about our partners is in the bottom of the slide. KTH has a plan to contribute with the modeling of thermomechanical behavior of partially ablated reactor pressure vessel wall in a Nordic boiling water reactor under hypothetical in-vessel melt retention. Yesterday, some results about that were already presented by my colleagues. We will use these vessel steel properties in our modeling, and we will have focus on the profile of ablation and on thermomechanical behavior. Also, we during IVMR project we provide more contribution into their benchmark exercises for PWRs with French type of reactor vessel steel, and we calculated preliminarily failure map for this case. So we are going to perform more modeling and to improve this map. In the IEA CRP in Coordinated Research Project for in-vessel melt retention, the first task is to develop phenomena identification and ranking table for in-vessel melt retention, to develop a validation matrix, and to select the best experimental data for model development and code validation, then to have quite large benchmark exercises with comparison between different codes for the different tasks, and also to carry out analytical benchmark on IVMR comprehensive scenarios. More details you will find here. There are many organizations from many countries which will be participating in this CRP. What is important to understand that IEA will provide small funding only for developing countries, the countries who are currently only at the beginning of development of commercial nuclear power program. KTH will contribute in paired with validation matrix, code-to-code comparison by safety analysis, Melcore modeling, modeling of heat and mass transfer in the stratified corium pools, and with thermomechanical calculation. Some KTH NPS experimental data can be suggested for the partners for the use in CRP. I would say generally that the extent of our contribution is quite dependent from our sponsors, as we are a university. There are ongoing research following up safest and IVMR. First of all, we are now doing, as I will show later, more detailed analysis from Quench SSM experiments, and also we will need to deliver SIMECO facility experiments and dedicated results. This is first time when I would show you the cross-section of bundle after Quench SSM experiment made in KIT. This is, by the way, also good opportunity to thank our colleagues from Swedish Westinghouse who provided materials for these tests. So you can see that the bundle is heavier damaged, and we have formation of eutectic melts in different parts, and also we have general deformation of bundle. So all this story will be carefully studied by post-test measurements, by post-test modeling, and then we are going to publish results. Maybe I can skip this slide because SIMECO 2 facility concept was already presented. Now a few slides about Fukushima progress with preparation of Fukushima Daiichi decommissioning and understanding of where is the fuel at Fukushima damaged reactors and how we can remove this fuel and what we need to do for that and to prepare for this corium reprocessing and final disposal. So for today, the general understanding and data about estimation of fuel debris distribution and properties in the units is still quite limited. So what you can conclude from this table, there are large ex-vessel corium masses in units 1 and 3 and less ex-vessel corium mass in unit 2. A small fraction of fuel remained in the core region of all units. There could be different locations of reactor pressure failure breaches in different units. Also, there is very large difference in the dose rates, and dose rate distribution is very ununiform if we will consider 3 reactors and different locations. For today, we have more advanced internal investigations in Unit 2, and we know a little bit more about corium in this unit. Strategy of our Japanese colleagues is mostly based on application of various robots, and this of course will need time, not only to develop robot and to test them, but also to have all the campaigns necessary at the plants. So there was a joint task force between OECD project to speculate a little bit what we can conclude from already obtained samples, to discuss and conclude from the analysis of the samples and analysis performed so far. I should say that all these samples mostly are very surface samples without going too deep to the bulk. And from the measured sample composition, we try to build preliminary conclusions which can influence our sample and post-test examination strategy. So what is visible, first of all, as concluded by GA and CLADS, we from the composition of sample, we see quite intensive interaction between U-zeta-O ceramic and metals, and that is a kind of quite important for the modeling, because that can contribute to liquefaction at much lower temperature in comparison with what originally expected. What we did here, we perform a comparison between samples from Unit 1 with their phase, which we calculated with the help of Melchor and nuclear. And we found that most dominant phase in our calculation, but also in their modeling, is cubic uranium O2, which actually is phase related to their original fuel. So basically, this phase in the sample can indicate lower temperature of corium in lower plenum than it is expected in modeling. Or the second possible explanation can be that equilibrium conditions were not reached, and we cannot completely trust to nuclear predictions. In general, their sampling and development technologies for their debris removal is going, I would say, still quite slow. And the plan for decommissioning was several times revised, and several milestones were prolonged. So the main important parts, the main important technologies are listed here. Of course, all these technologies for sampling and investigations are based on various robots, and I recommend you to visit TEPCO sites, and there you will see a lot of interesting information how these robots are progressing now. For the removal, the previous slide was for the sampling and sample removal. For the debris removal, it's much more work needed for development of different systems, and all these works, of course, will be highly dependent on the results of debris study and debris sampling. Coming to the conclusions, I should say that severe accidents are the focus of considerable research worldwide under coordination of different international organizations, because there are too many challenging physical phenomena, complicated further by high temperatures, radioactive materials, technological difficulties, and it is quite clear for today that no single country has sufficient resources, both human and financial, to do everything. Because of that, we believe that this international collaboration becomes extremely important in severe accident research. Joint efforts and large R&D programs coordinated by OECD, IEA, and other organizations are very beneficial for all participants. I believe personally that national program, APRI program, is proven to play a very good role, and it is promoting the competence, and it is quite influential even in the context of international arena. Many FDNPP forensic investigations now are in good progress, but limited corium sampling, which has strong technical and regulatory challenging, as well as more urgent site activities like removal of spent fuel, difficulties and cleaning of contaminated water. All these plant activities, of course, slowed down sampling of corium, research missions, and preparation of decommissioning. I personally have some belief that, like after TMI and Chernobyl accident, post-Fukushima studies and site decommissioning, rehabilitation will probably need more time than originally expected. We are very grateful not only to our sponsors, but also to many colleagues contributing from many organizations contributing to general progress in severe accident research. Thanks a lot for your attention. If you will have interest to learn more, we also prepared an annex for you with the recommended literature, which is available through internet. Thanks again.
Thank you very much, Sebastian, for this comprehensive, informative, and interesting presentation. I also fully agree with your conclusions. Unfortunately, for the sake of time, I'm not able to provide any questions to you. Otherwise, it will be difficult to keep our time schedule. But anyone who is interested in asking questions to Sebastian is encouraged to put them in the chat, and we will distribute them to Sebastian and try to provide you with an answer.
Yeah, I will try to do that. Thank you.
Thanks again, Sebastian. And now I would like to introduce our next presenter, Dr. Christian Linde. Christian is my colleague at SSM, and he is an analyst responsible for chemistry during severe accidents. And he is also a new member of APRI steering group, replacing Ninos Garis. And as one of his tasks in APRI, Christian has been covering different OECD NEA projects related to source term issues. So please, Christian, go ahead.
Thank you. Let's see now. Okay, I hope you're able to see my slides.
Yeah, we can see them. Thanks.
Yeah, thank you. I will switch to Swedish for this talk, but all my slides will be in English, so I hope you will be able to follow from there. Så ja, som Patrik nämnde då så har jag precis inträtt i APRI styrgrupp. Jag har även tidigare varit med i den så kallade referensgruppen som har följt arbetet på Chalmers då inom APRI-programmet. Och där ingår ju även representanter från alla parter i APRI. Och det är också ett extra hedrande uppdrag ska jag säga, eftersom jag själv har en kemibakgrund från KTH då, så att det är trevligt att se vad som händer på andra sidan landet också. Men som sagt, den här bevakningen då gäller ju då de internationella projekt som APRI har varit med och finansierat då. Och vi har inte haft någon egen aktivitet i de här projekten, utan det rör sig då om bevakning av det pågående forskningen där. Och jag kan säga det att inom TAI 3 har ju även Johan Ljung från Ringhals deltagit i bevakningen då. Vi kan även säga att Chalmers har ju lämnat viktiga bidrag inom framförallt jodkemi då till de tidigare BIP-programmen och på senare tid även lämnat betydande avtryck även i STEM-forskning då. Jag återkommer till det. Jag tänkte vi skulle börja med att göra en liten introduktion kring jod som är egentligen det stora temat för de här 3 projekten. BIP handlar just om jods beteende, STEM handlar om källtermsutvärdering där jod och ytterligare några fissionsprodukter studeras då. Och TAI som i huvudsak sysslar med termohydrauliska experiment där vätgas är en viktig komponent. Men även där är jod ett studieobjekt då. Sen några korta ord om 2 nya projekt som kommer starta inom TEMIS, inom OECD, det är TEMIS och Ester då, som håller på att rulla igång. Om vi tittar nu på de huvudsakliga syftet då med den här haverikemin som vi sysslar med, det är ju då att få en förståelse för de kemiska fenomen då, som ger möjlighet att påverka framförallt hanteringen då av ett svårt haveri. Och det handlar ju om att skydda omgivningen då och minska utsläpp i stor utsträckning som möjligt då. Och det som sker i skrubben är naturligtvis, i haverifiltren är givetvis ett väldigt bra exempel på hur kemin kan göra arbetet då när det gäller att skydda omgivningen. Andra fenomen då, som bildandet av vätgas, kan ju också medföra utmaningar då. Det är ju kemi som ligger bakom även de processerna då. Sen har ju haverikemin väldigt betydelse då naturligtvis för att kunna göra säkerhetsanalyser och göra källtermsförutsägelser då. Så att utveckling av beräkningskod är ett viktigt moment då, och till det behöver man ju då data från experimentell verksamhet. Och ja, som sagt, jod är ju då det stora huvudämnet för de här 3 programmen då, och det har ju fängslat en forskarvärld under en längre tid, får jag lugnt säga. Jag tänkte börja med att dyka ner i ett periodiskt system. Här så hittar vi ju jod näst längst till vänster här i gruppen som kallas halogener. Den är ju granne då med ädelgaser som en annan typisk fusionsprodukt. Xenon och krypton är framförallt representanter där. Och längst till vänster har vi då alkalimetaller som också är, där vi hittar cesium då, som är också en viktig fusionsprodukt. De här 3 grupperna skiljer sig rätt väsentligt då när det gäller framförallt reaktivitet. Och halogener då som jod har ju väldigt rik kemi då, och därför vi har nu spenderat många års forskning kring det här. Ädelgaser är ju tämligen ointressanta i det avseendet, de är ju helt inerta. Och alkalimetaller har ju egentligen inte alls den rika kemin, även om de är viktiga som cesium då, som fusionsprodukt då. Jod har ju då 2 egenskaper, skulle jag säga, som är väsentliga. Dels flyktighet och löslighet då. Och det här är 2 viktiga exempel. Grundämnes elementär jod då, helt enkelt, som är en vattenlöslig förening men också en väldigt flyktig förening då. Den sublimerar ju relativt snabbt. Det är ju kristall vid rumstemperatur, men den sublimerar ju vid upphettning då och bildar en ånga, jodånga. Cesiumjodid är ju en annat exempel då som inte alls påminner om den här violetta ångan som vi ser till vänster då, utan det är ett salt som är väldigt, väldigt lösligt i vatten. Och här har vi dessutom cesium då, som är den andra viktiga fusionsprodukten då. Det finns ju andra former, aggregationsformer som man kallar det då, som är viktiga i det här sammanhanget då, och det är ju vattenlösliga former, eller former som föreligger i vattenlösning, antingen lösning eller som suspension eller som utfällningar då. Aerosoler är ett begrepp också som är viktigt när det gäller jodkemi. Och aerosol är egentligen en lösning i luft, kan man säga, en aerosolution. Och det är en suspension av fina, antingen fasta eller vätskeformade droppar då i luft. Hur var det nu då med den här rika kemin? Jo, det är ju så att jod har ju väldigt många oxidationstillstånd tillgängliga. Och som ni ser av den här bilden så har vi då väldigt stora möjligheter att bilda väldigt många olika föreningar. Vi hittar ju elementär jod längst till vänster i 2 som har oxidationstalet 0, och sen har vi jodider som är en viktig form också, oxidationstal -1. Sen har vi ett stort begrepp som kallar vi jodoxider som återkommer också. Det är ett samlingsnamn för alla de föreningar som är, om man säger, oxiderade till högre oxidationstal här. Om vi jämför med cesium så har vi egentligen bara ett oxidationstal, nämligen cesium plus 1 då. Så där är kemin betydligt mer begränsad, men där är viktigt att komma ihåg att den motjon som krävs då till cesium plus är ju den som kommer ge cesium dess egenskaper egentligen. Nu är det ju inte det här det enda, utan vi har ju även en grupp som kallas för organiska jodföreningar, och det är ju representeras ju framförallt av metyljodid som är den enklaste formen. Och det finns ju mindre organiska jodföreningar som liknar metyljodid, etyl och propyljodid, och även former av lösningsmedlet aceton, jodaceton. De här har ju kännetecknats också av att de är väldigt flyktiga, och de är inte särskilt vattenlösliga heller, och det gör att de inte är särskilt reaktiva i vattenlösning heller, utan de här beter sig snarast som ädelgaser, skulle man nog säga, i vattenlösning. Och det gör ju då att de placeras den här skrubben i stort sett oförändrade, och det kan ju vara ett problem. Om man då sammanfattar jodkemin då, det här är lite förenklad bild av hur jod kan uppföra sig i vatten- och gasfas. Och det som är viktigt är att komma ihåg att det är en mängd olika processer som pågår i både vattenfas och gasfas. Och det centrala är ju då egentligen de processer som leder till flyktiga former av jod. Det är alltid mycket enklare att ha kontroll på de föreningar som befinner sig i en vattenlösning än de som befinner sig i en gasvolym. Och här då bland de flyktiga formerna så finner vi då elementär jod, organiska jodföreningar och de så kallade aerosolerna då, som ofta representeras av jodoxider då. Och det är viktigt att alla de här processerna pågår ju kontinuerligt i olika omfattning och är beroende av dels temperatur, även radiolytiska förhållanden i både gas- och vattenfas. Surhetsgraden i vattenfasen är viktig, så kallade pH-värdet då. Där visar sig att ett högt pH-värde trycker ner de flesta jodföreningar i vattenfasen, vilket är att föredra då. Så då ovanpå det här har vi även sönderfall av de här radioaktiva komponenterna. Så det komplicerar ju bilden givetvis ytterligare här då. Så om vi nu går in på jodprojektet här då, eller för det var BIP-projektet som heter just Behavior of Iron Project, där man tittar då på beteendet hos jod, och det har varit den kanadensiska Canadian Nuclear Laboratory som har varit operating agent som man kallar då, och som har utfört de försöken i det här programmet. CNL då ligger då i Kanada som sagt och har en lång historia kring forskning kring jod framförallt. De har ju den nyligen nedlagda NRU-reaktorn som har varit en stor producent av medicinska isotoper genom åren. Man har även egen tillverkning av jod 131 då, som man har kunnat använda i de studier som man har genomfört här. BIP-programmet började redan 2007 och har genomförts nu redan i 3 faser med en grupp länder då som har deltagit. Det här är partners från det senaste BIP-3-programmet då. Och ska se. Så syftet med det här programmet har ju varit att undersöka då separata effekter i jodsbeteende under svåra virförhållanden då. Och sen då för att använda de här resultaten i modelleringsstudier som analytiska modelleringsstudier. Det som skedde i det första BIP-programmet var att man kombinerade resurser från partners då för att skapa en samlad förståelse för hur jod beter sig och även andra fissionsprodukter. Man hade specifika mål, det gällde kartlägga då den totala processen för organisk jodbildning och kvantifiera då bidragen från olika processer. Dels i vattenlösning då och dels i porer på färgytor och även heterogena processer på ytor då, som ger upphov till organiska jodföreningar. Och här handlar det mycket om att mäta då hastighetskonstanter för olika individuella steg i de här processerna. Adsorption och desorption är ju då hur ämnen övergår från gasfas till en yta då, eller omvänt. Och allt det här samlat inkluderar även då experimentella försök som blir tillgängliga för deltagarna då för fortsatt utveckling av förståelsen. När man nu gick vidare till BIP2 som var den andra fasen, då man hade ju insett att man behövde en mer detaljerad och mekanistisk förståelse för dels bildandet av metyljodid framförallt och även då det som föregår bildandet, adsorptionen då på ytor. De här nya experimenten krävde också att man hade mer väldefinierade färger då för att förstå på en mer detaljerad nivå vad egentligen som sker. Och man tog till också nya instrumentella tekniker då för att mäta dels morfologin, alltså ytans utseende, och sen titta på hur djupt jod då tränger ner i ett färglager då. Och det hela handlar ju om att utveckla en gemensam förståelse för hur man sedan då extrapolerar de här resultaten från de här mindre experimentella skalan då till en reaktorskala. Och några slutsatser som man drog då från BIP1 och BIP2, det var ju att man hade fått bättre förståelse för separata effekter som kunde ligga till grund för modellstudier. Och sen kunde man ju se att målade färgytor är ju väldigt viktig, vad ska kalla för jodsänka, eftersom det är en väldigt stor yta i en inneslutning som är målad. Så att en stor mängd jod kan alltså deponera där under olika förhållanden och sedan då konverteras till organiska jodföreningar. I det tredje försöket då så vill man ju då förbättra möjligheten att kunna simulera de här processerna, adsorption och desorption på inneslutningsytor. Man vill också kunna förutsäga metyljodid, framförallt då bildandet och uppförandet, både bildande och degradering under haveriförhållanden. Man vill också undersöka åldringens effekt på de här processerna. Färg åldras ju som bekant med åren då, och hur det kunde påverka då både adsorptionen och bildandet av metyljodid. Ytterligare studier inriktade sig på olika reaktiva gaser som kan bildas under haveriförhållanden då, och hur det påverkar dels färgytor och andra processer. Och här har man nu då gjort en gemensam insats och bildat en analytisk arbetsgrupp då som tar vara på data för att arbeta in i sina beräkningskoder då för att kunna genomföra de här simuleringarna. Åldringen av färg då, den kan ju ske, eller där genomför man ju prover då, dels naturligt åldrade prover. Men också artificiellt åldrade genom termisk härdning då, eller genom bestrålning, så man bestrålar färgprovet innan man genomför experimenten då för att se på ett sätt kunna simulera åldring då. Det som först sker då är adsorption på en målad yta, och den här generella modellen beskriver egentligen att hur jod adsorberas på ytan. Beroende på hur länge man väntar så kan vi få olika tjocka lager. Då. Tidigare trodde man kanske att det var ett begränsat antal säten egentligen på färgytan som fanns tillgängliga, men givetvis det innersta lagret som kommer en direkt kontakt med den målade ytan. Då. De här testerna utförs i en mindre glasbehållare där man fäster sina så kallade färgkuponger då och sluter till och sen injicerar isotopmärkt jod 131. Det använder man då för att genom att mäta dosraten så får man en bild av hur mycket som adsorberas på ytan då. Och några av de slutsatser som man kunde dra här när det gäller just åldring då, att nymålade ytor ger ju den högsta produktionen av metyljodid då man bestrålar ytan då som är deponerad med jod. Och det är ju en viktig slutsats då att det blir ju inte värme i tiden här utan färgen blir alltså mindre och mindre benägen att bilda organiska jodföreningar med tiden då. Och det visar sig att åldring då förstör egentligen den här polymera färgstrukturen och det leder ju då till att man får urlakning av organiska, framförallt små lösningsmedel, flyktiga lösningsmedelsmolekyler då, som kan fly ur den här färgstrukturen. Och kvarblivna lösningsmedel är egentligen en källa som man inbillar sig då som ger upphov till bildandet just av organisk jod. Åldringen då, ja den påverkar också absorptionshastigheterna på de här ytorna. Men sen visar det sig även att färg, man nu fokuserar väldigt mycket av den här forskningen på just färg, men även annat organiskt material kan ju genomföra samma process och bilda metyljodid har ju visat sig. Och det blir man ju varse om när den här tätningsringen som satt kring det här experimentuppställningen då även bidrog till bildandet av organisk jod. Men det kunde man få kontroll på i varje fall, så det påverkar ju inte resultaten. Men det är viktigt att påpeka det. STEM är då ett projekt som har letts av IRSN i Cadarache i Frankrike. Och det är egentligen ett systerprojekt till BIP. Där jod är en av de studieobjekten i det här projektet. Då. STEM har genomförts i 2 faser, började 2011 och med stort sett samma partner som har deltagit i BIP-programmet. Även här har det funnits en analytisk arbetsgrupp då, som har jobbat med de experimentella resultaten. Så syftet har också varit här att förbättra förmågan och uppskatta storleken på källtermen som i samband med en radiologisk nödställssituation då, och reducera de osäkerheter som finns kring vissa kemiska fenomen. STEM har väl haft en liten annan inriktning när det gäller jod. Då är det framförallt jodbärande aerosoler som man har valt att titta på, alltså de här luftburna dimmorna eller dammfenomenen. Och hur de beter sig i inneslutningen. Här inledde man också försök med ruthenium som angränsar givetvis till de försök som Chalmers utförde på tidigare stadium tillsammans med VTT i Finland. Så att det var tre huvudfrågor kan man säga i det första STEM-projektet. Dels frigörande av jod, speciellt med fokus på jodaerosoler som jag sa då. Och så även titta på hur dessa påverkas av bestrålning och hur de sönderfaller då. Och hur det kan bidra till bildande av gasform i jod. Även här har interaktion mellan jod och målade ytor varit under en del av experimentella verksamheten. Då. Och när det gäller rutenium så är det då transport i primärsystemet som är det centrala, som liknade det som beskrevs igår av Chalmers, de som nu tittar på tellurkemi. Den här bilden visar den experimentuppställning som man använder för de här studierna med organisk jod. Det kallas för APRI då. Här har man då en strålkälla, en kobolt 60. Och sen ett slutet system där man den bildade organiska joden här kan transporteras vidare då till en detektor MAPAC-filter här då, där man sköter detektionen online då. Så att man får en realtidsuppskattning av hur organisk jod bildas då. Här har man även möjlighet att införa olika bärargaser och påverka till exempel luftfuktigheten eller sammansättningen då av bärargasen. Rutenium-experimenten genomfördes ju då med en rörugn som påminner om den som Chalmers också utnyttjar då. Där man helt enkelt hettar upp ett prov under ett flöde av olika gaser och ser hur långt de transporteras och i vilken form som de uppträder. De här experimenten har ju gett då naturligtvis bättre förståelse för interaktionen mellan elementär jod och metyljodid under bestrålning. Även då bildande och radiolytiskt sönderfall av jodoxider då i både gas och aerosolform. Och sen även hur radiolytisk omvandling av gasform i elementär jod och sker till metyljodid. STEM 2 sen har ju då gått vidare med de här undersökningarna då, och det rör dels åldringseffekter på målade ytor då vid lite högre stråldoser och sen jodoxiders fortsatta sönderfall då till flyktiga jodformer och ruteniumtransport i primärsystemet var ju också då en punkt på det här programmet. Man drog ju samma slutsats det här som i BIP-programmet egentligen att åldring av färg har inte någon betydelse. Det var lite olika typer av färg som man har jämfört här då. Men mönstret går igenom då samtliga typer av färger. Och sönderfallet av jodoxider kan ske då dels radiolytiskt och dels kemiskt inducerat. Och där tänker man att då det kan påverkas då av olika gaser då, till exempel kolmonoxid och vätgas då som finns i atmosfären. För rutenium har man gjort då en variation av olika betingelser och även jämfört med resultaten från Chalmers och de visar ju god överensstämmelse även om betingelserna skilt något då. Om vi går vidare då till TAI-programmet så hade vi där Becker Technologies i Eschborn utanför Frankfurt som var operating agent för det här programmet. Och här rör vi oss kring termohydraulik, vätgas, aerosoler och jod också. Och här handlar det egentligen om fenomen då som är kopplade just till de här vätgas, jod och aerosoler då i inneslutningen då vid svåra haverier. Och vätgas är framförallt intressant för att se vilka utmaningar då som kan uppstå mot inneslutningens integritet då. Det här är ett lite större program. Det har också gått i 3 faser sedan 2007. Det är betydligt fler partners som har varit med i det här programmet. Här hittar vi bland annat Indien och Kina som inte har deltagit. tidigare i andra program, och även Luxemburg. Det är första gången som de har deltagit här då. Även här hade vi en analytisk arbetsgrupp då som utvärderade de data som kom ur experimenten. Budgeten har också varit lite större. Det är bortåt 100 miljoner kronor som man har spenderat på de här försöken i TAI-programmet då. Den här bilden visar ju då TAI-anläggningen. De första 2 programmen så var det då en behållare på ungefär 60 kubikmeter som användes då för de här försöken. Den byggdes sen till då till det 3:e programmet med ytterligare en mindre behållare som kunde anslutas då till den första. Den kallas då för TAI Plus anläggningen då, efter den här uppgraderingen då. Den har även ett populärt smeknamn då, PAD-TAI, där PAD står för Parallel Attachable Drum, som är den mindre behållaren då på 18 kubikmeter. Men i det första programmet så gjorde man en del inledande försök där man tittar på hur man kunde använda helium då som en ersättning för vätgas i de försök där man inte ville riskera en vätgasförbränning då. Just för att titta på flödesdynamiska fenomen, ska jag säga. Vätgasförbränning har annars varit ett studium då. Där vill man titta på tryck och temperaturförlopp och även hur snabbt flamman då propagerar i en luftvolym eller i en inneslutningsvolym. Vätgasrekommendatorer, ska vara parutrustning, har ju också varit föremål för olika försök. Och de är viktiga framförallt i luftfyllda inneslutningar där man då vill rekommendera vätgas och syrgas då under kontrollerade former. Och redan vid låga koncentrationer, ska jag säga. Här vill man titta även på hur metalljodider kunde interagera med parutrustningen, till exempel cesiumjodid då. Förgiftning av parutrustningen är också någonting som man ville se hur robust funktionen är då egentligen. Sen nedspolning via spray då, hur aerosoler kan tvättas ner ifrån ytor. Det är också en topic då i den här serien. TAI 2-programmet gick vidare med ett antal aktiviteter. Och jag ska säga att Tyskland kör ju även ett nationellt program i samma anläggning som har bidragit med resultat till det här TAI-programmet, där man har tittat på lite andra frågeställningar då, eller angränsande frågeställningar. Men i TAI 2-programmet så gick man vidare med studier kring vätgasförbränning och interaktionen med spray. Sen parutrustningens beteende då vid låga koncentrationer. Man vill ju se när den här rekommenderingen, vilka koncentrationer den startar. Och sen hur den hastighet som rekommenderingen sker med dem. Sen ett antal försök som involverade jod och interaktion mellan jod och aerosoler. I det 3:e programmet då, där man hade då tillgång till den här TAI Plus-anläggningen, där gick man ju och tittade på hur parutrustningen beter sig under vad man kallar för motströmsförhållanden. Det vill säga där man har ett flöde som inte sker rent konvektivt då. Och i och med att man har 2 behållare som även möjlighet att titta på hur vätgas förbränns då i det här 2-kammarsystemet då. Och hur flamman propagerar mellan de två behållarna och de fenomen som man kan upptäcka där. Man har även genomfört försök då hur fissionsprodukter övergår från vattenfasen då under förhöjda temperaturer. Och där är det framförallt elementär jod som visar betydligt ökad benägenhet att gå upp i gasfas vid uppvärmning. Då. Sen även försök där man tittar på hur deponerade fissionsprodukter påverkas av en vätgasförbränning. Och de här skisserna beskriver ungefär hur den här anläggningen kan varieras då för att genomföra den här typen av försök. Det här beskriver då hur försöken där man tittar på motströmsflöden kring parutrustning då, hur de genomförs. Det sitter en liten fläkt i det här övergångsröret längst ner då som sätter hela volymen i rörelse här då, och man kan få ett flöde som går uppifrån och ner kan vi säga på vänstersidan här. I den här utrustningen finns gott om mätutrustning i olika punkter, bland annat tittar man på luftfuktighet, man tittar på tryck och temperatur i olika positioner och även vätgaskoncentration då, för att se hur det här fördelas då. Det visar sig då att de parutrustningar som man tittar på var inte särskilt känsliga för den här typen av avflöde då. Utan de fungerade ungefär som de borde då. När man tittar på förbränning mellan två system så kan man ju även där dels testar man ju då hur man antänder den här volymen vid olika positioner då av den här volymen. Man kan använda en stratifierad lösning, alltså där man har en gradient, koncentrationsgradient i den här behållaren då. Även här mäter man temperatur och tryck och luftfuktighet i olika positioner. Och här visar ju sig naturligtvis att flampropageringen accelererar då givetvis i övergångsröret här mellan behållarna. När man tittar på experimentsutställning för fissionsprodukters återinträde i atmosfären så använder man den mindre behållaren då som försöksbehållare, och den större behållaren utgör egentligen bara en uppsamling av de radioaktiva jodkomponenter som man förflyktigar då i den vänstra behållaren. Och här låter man då en luftvolym bubbla igenom och under uppvärmning då. Här kan man även titta på med hjälp av kamerautrustning då på de här bubblornas färd upp genom vattenvolymen. Och här är då dels både metyljodid och elementärjod som man använt för att jämföra här. Återsuspendering av alltså deponerade fissionsprodukter vid en vätgasförbränning har man också tittat på. Här har man istället färgkuponger då som med deponerad jod till exempel då, som man placerar på olika positioner i den här kammaren medan man sätter igång en vätgasförbränning då. Så Temis då slutligen är ju ett av de nya projekten då som kommer att starta här. Som har redan tjuvstartat ska jag säga strax före jul. Och det är fortfarande Becker Technologies som kommer utföra försök i den här TAI Plus-anläggningen. Och nu tittar man på en del kvarvarande frågeställningar och som då relaterar fortfarande till vätgas och fissionsprodukter. Och det är under förhållanden som uppstår vid MCCI, alltså betongsmälta interaktioner. Och här är då de gaser som utvecklas vid MCCI, både vätgas och kolmonoxid som man vill titta närmare på hur det påverkar parutrustningen. Även förbränning och flampropagering då i närvaro av en blandning då av vätgas, kolmonoxid, ånga och luft. Det andra topic där. Jodoxider kommer också ingå i den här studierna. Hur de interagerar med andra aerosoler som uppstår i samband med MCCI och hur de aerosolerna kan fungera som bärare av olika jodföreningar. Då. Sen frågan hur fusionsprodukter kvarhålls i vattenföreningar eller i vattenlösning är fortfarande ett viktigt tema här då. Begreppet pool scrubbing då, det är någonting som man vill titta på. Sen avslutningsvis ett par interaktioner med jodoxider och de här aerosolerna i en atmosfär av vätgas och kolmonoxid. Det är ju ett integralt experiment kan man säga, där man kombinerar de här olika försöksserierna då i ett enda experiment. Avslutningsvis då, Ester är ju då ett projekt som IRSN kommer att driva vidare i samarbete med CEA, och det bygger vidare då på även detta då fördröjda fenomen, fördröjda utsläpp av källtarm då. Och det handlar framförallt om remobilisering, att deponerat material som sätts i rörelse då. Man kommer då utföra analytiska tester då av enskilda fusionsprodukter för att studera dem var för sig då. Och här har vi även tellur då på menyn tillsammans med cesium, olika sorter. Sen genomför man då semi-integrala tester där man ser på kopplade effekter mellan olika fusionsprodukter, bland annat cesium, jod och molybden. Och ett avslutande test kommer genomföras med då autentiskt bränsle, får vi kalla det, från CEA då, som tillhandahåller då man kallar för riktiga deposits av fusionsprodukter då, för ett mer autentiskt test. Sen fortsatt tema då kring organisk jodformering då från flyktiga organiska föreningar, och nu tittar man framförallt då på små lätta organiska föreningar som metan, aceton och etylen. Och man har även stoppat in ett experiment som handlar om isoleringsmaterial som också är organisk förening. Då. Så avslutningsvis kan vi säga att alla de här 3 programmen har ju verkligen vidare belyst de här komplexa fenomenen och processer som man har studerat. Framförallt jod, men även andra fusionsprodukter. Och man har fått en förbättrad förståelse för de här fenomenen, kan jag säga, och hur de kan då påverka radioaktiva utsläpp under ett haveri. Programmen har även bidragit med väldigt mycket data då, som kan användas i kodutveckling, och det är ett viktigt moment, får man säga, i de här programmen naturligtvis, att man arbetar med de resultat som kommer ut för att på så sätt bilda sig en förbättrad förståelse av de olika processerna. Och det här har givetvis också gett då 2 följdprojekt då, som kommer ta upp kvarvarande frågor. Och sen är det viktigt med de här internationella samarbetsprojekten där som kommer till alla partners till godo med hjälp av en delad kostnad naturligtvis. Och med det var mitt sista ord. Tack.
Thank you very much, Christian, for guiding us through these complicated experiments. Very informative and comprehensive. Unfortunately, we're out of schedule, and I will not pose any questions to you, unfortunately. And we were supposed to have a break, but in the sake of time, we will continue directly to session number 6. And I'm very happy to introduce our keynote speaker, Randy Jaunt, who is a knowledgeable senior researcher in severe accident. And he has been, he retired recently before he was the manager of the Melco development at Sandia National Labs. And Randy has participated in many international projects. And he has been so kind to record a movie for us, since there is a time zone difference between Sweden and Albuquerque, where Randy lives. So we will start this movie, and after the movie, Randy is online to take questions from the audience. So to our technician, could you please start the movie now?
Okay, greetings everyone, and thank you for inviting me to give the keynote speech to this, I guess it's the last current conference of the APRI 10 workshop, and I'm really happy to speak to this group. My name is Randy Gant. I am somewhat recently retired from Sandia National Laboratories, and Patrick, who invited me to do this presentation, kind of asked if I could focus a little bit on the modeling practices and in particular insights gained in our severe accident analyses of Fukushima. And so the title of this presentation is Modeling Severe Accident Progression 10 years after Fukushima. And I plan to draw on some modeling examples there. So the highest level objective that I have here is to illuminate some of the key severe accident phenomena that have been found operative in the Fukushima analyses, and to kind of draw a line of sight between some of the fundamental science data and the practical application of systems analyses through severe accident codes. And to do this, I'm going to draw upon some examples from our Fukushima forensics analyses. I have a list of phenomena. I'd like to talk about suppression pool thermal stratification, something that kind of jumped out at us in looking at containment response. These phenomena are actually presented a little bit in chronological order as you may encounter them in severe accident timeline. And one that's kind of interesting from a fundamental simple engineering standpoint is the dry well head flange leakage under excessive pressure. We'll take a look at that. It's an interesting problem. Then I want to point out some things we observed about hydrogen, not so much generation, but its behavior in the reactor building leading to the observed explosions in units 1 and 3. And I have an interesting story to tell you about that one. Then I would like to move on to some of the, I guess, still persistent mysteries in Fukushima, and in particular, lower head response and melt progression leading to vessel head failure. We will look at some of the key mysteries that have been revealed by entry into the containments and ponder what do we need to do about any of this in severe accident modeling. I had wanted to cover more on molten core concrete interactions, but time permitting, I'll point out where we think we saw it, where we think we didn't in the forensics analyses. And then I want to conclude with some words on uncertainty propagation. I know that subject has been touched on before in this group, but it's a really important concept. And so I want to leave you with that discussion on uncertainty. I like to use the word propagation. because we're going to propagate uncertainties through a code analysis. And then I'll just express best wishes and good luck to you all. Let's see what's next here. I've got this slide I've used before. I call it the timeline of nuclear safety technology, which basically chronicles some of the key events over the past several decades, 50 years really. Some of the key accidents you see here, 3 Mile Island and Chernobyl. And in particular, the accident at 3 Mile Island precipitated a lot of fundamental research, such as being presented at the APRI 10 conference as well. And this has resulted in the development of integral systems codes for use in predicting the behavior of severe accidents. Some of the notable ones, Melcor code, which I worked on for years at Sandia, MAP, which is the industry standard, and Aztec is a popular European computer code as well. And so those are the like repository of knowledge. As we do this research, information gets invested into the computer codes, and then we can apply them to problems that may emerge. So this picture here shows a kind of schematic. There are a lot of versions of this. Every code group has one, but it illustrates the multi-simultaneous phenomena that are actually coupled and ongoing in a severe accident, including thermal hydraulics, core heat up, hydrogen generation, hydrogen burns, and so forth. And we're going to investigate, we're going to take a look at several of these phenomena that are treated in the codes and see how that goes. 2 more slides in this introduction here. This one shows of course, the famous Mark I Taurus containment design, and 2 aspects I want to point out about this. You see the suppression pool here. It's pretty large, and it's like a small lake and a huge thermal heat sink. This suppression pool can soak up decay energy for quite a number of hours before it saturates. But how the decay energy gets into the suppression pool, generally by 2 ways. The safety relief valves will discharge into the suppression pool, and they are situated azimuthally, they vent azimuthally around this pool. And then the other thing I want to talk about is this large closure head that sits atop the containment. Here you see this guy sitting at the top of the containment. And if you look closely, you can see many bolts attach this head to the containment. And while there are obviously many places that a containment leakage could take place, this head is one of the principal regions where you will get a containment leakage from overpressure. Interestingly, not a catastrophic failure. We're going to talk about both of those in the next couple of slides. And then finally, here's the picture you've seen before on the in-vessel fuel and structures within the reactor pressure vessel. And when we get to the part of this presentation where we discuss the interesting core damage remnants that have been cited in the cavity region, we're going to find that elements, some intact core components from the core and some interesting intact components that were previously in the lower head are now visible, very visible. They're not slumps of molten mass. They're obviously intact components, and we're wondering how did they get there. So we're going to pause. I'm going to pause here briefly okay. The topic of suppression pool stratification, this is a large component and spatially very large. And I'm just to make the point here, I've got a very simplified diagram, which shows the Mark I, it shows the suppression pool sitting down here. And as I mentioned earlier, the SRV tailpipes from the cycling SRVs drop down and vent into the torus region, and they are spread azimuthally around the torus. But the way this works is when relieving pressure, it's the lowest set point SRV that cycles, and so most of the steam being vented from the RPV will leave this single low set point SRV and begin to accumulate decay heat in the suppression pool. Now, being locally injected into the pool, you can develop a stratification where the lower density hot water that has been discharged into the pool tends to float up and reside at the upper level. So you have a hot layer. I'm showing it in this picture on the right here, showing it slightly red, and a cold layer. So the decay energy is not uniformly mixed in the suppression pool. So what happens is the containment pressure now follows the saturation pressure of this hot layer, as opposed to the saturation pressure of a well-mixed pool. This threw us for a while in the analysis of the Unit 3 because people didn't quite realize this was happening, and some creative solutions were explored to supplement the steam to the dry well to try and better match the pressure response. This has kind of not been broadly appreciated by operators. I had interesting discussions with Browns Ferry specialists where they did see this stratification before. And it's generally not captured presently in the severe accident codes, but it has a lot to do with predicting the pressure response of the containment. So I just hold that up as something to think about. Okay, kind of related to this is an interesting problem. Going back to that dry well head flange, this next group of slides will focus on the containment response to overpressure. You'll like this because it's really very much of a second-year engineer stress strain problem. Okay, recall the dry well head over here in the, I believe this is a Browns Ferry construction photo. There's the head. It sits atop the containment up here, and here's my engineering textbook representation showing a bolted head that is under pressure, and therefore the bolts are beginning to see some counter stress due to the growing pressure inside the containment. Well, what happens is the bolts will eventually begin to stretch as that internal stress exceeds the closure stress on the bolts, and the head flange will begin to part. And you can see in this stress strain curve here, this is the famously recognizable elastic region of the curve, where if you load the system up, it will strain, and if you unload it, it will unstrain. And then here you recognize the permanent strain or deformation. And probably both of these are happening when these head bolts get stretched under pressure. But basically, the leak area associated with separating this flange ends up being pretty much proportional to the pressure. So this is the model. We actually developed this model back in the Sorka days and applied it to the analysis of the Fukushima. And I show here, this is a little bit of a dated study, but we did this at Sandia in 2012. And it shows the dry well pressure. There are data from the accident progression that are shown there in the black squares, and then the black line is the calculated response. And a couple of notable things here. Sandia predicted a main steam line rupture at this time, and here you see the depressurization of the RPV into the containment, and here's this spike from the steam line rupture. It is known that the RPV was depressurized. They just don't know how quickly it happened. In our analysis, this is the lower head failure time, and you can see that materials dropping into the cavity cause another surge of pressure, and then they just roll up here and go flat. And where they roll up here and go flat, this is the period of time of the PCV head flange leakage. And I may not have pointed it out, but in this model, if the pressure continues to increase, the area will open up, which will decrease the pressure. So it very much, the bolt stretching very much acts as a pressure regulator. And you see that pressure regulation here in this plateau along the way. So this head behavior was leaking and releasing fission products and hydrogen to the reactor building for more than 10 hours until containment venting was finally accomplished. And here you see the containment pressure then falls. In our simple model, when the containment pressure falls, the leak area closes up and the leak terminates. Now, one other thing I'll point out here is a point where the containment pressure is seen to suddenly fall, and this is about the time that in this analysis we predicted PCV liner failure from core concrete interaction. This would seem to us to be consistent with our current views on core molten concrete interaction. Okay, so we've seen that you overpressure the containment and the dry well head flange can leak. And I mentioned that when the head flange opens up, contents within the containment will leak, including fission products and hydrogen. And so the next few slides kind of pick that situation up. And I'll just show something here that shows the Melcor predicted, again, this is for Unit 1, the Melcor predicted core damage. And in this analysis, really, Unit 1 proceeded quite without any mitigative actions at all. And core damage, therefore, began after around 4 hours and continued through progressive fuel melting at about 6 hours with high core exit gas temperatures, as well as fission products and hydrogen going into the reactor building. So this picture shows from that same analysis the hydrogen generation in Unit 1. And so just look at this green curve here. This is the in-vessel hydrogen from the oxidation of zirconium cladding. And it kind of proceeds in steps here depending on the core degradation. But you can see that upwards to 1,000 kilograms of hydrogen can be generated just in vessel. We used to take this story to the BWR owners group operator training, And I found that operators were always quite astonished at what the volume of 1,000 kilograms of hydrogen would be. And just to kind of bring that point home here, 1,000 kilograms, that's roughly the in-vessel, kind of quantity. At standard temperature and pressure, occupies 12,000 cubic meters, or about twice the volume of the Mark I containment. So you can see that these are huge volumes and will produce containment pressurization. I include this figure. It's related. What this is the actual mass flow rate calculated to exit through the separated head flange from containment overpressure. And that's the blue curve here, and it shows that, well, in this case, we had the initiating event of lower head failure around 15 hours, and you can see that there was a sudden burst of release and then this constant mass release over about 10 hours or so, as the head flange is separated and the leak area opens up. To try and convince you this is actually happening, I'm also showing here the dose rate obtained at the front gate, which is kind of picking up the air dose associated with leakage. And these two are very consistent in timing. The time that the code predicts containment leakage is roughly the same time that airborne radioactivity is seen. Now, this airborne activity is up in the air, so it's not falling away. When the operators vented the containment, of course, the pressure dropped and the head flange leakage in our ideal model terminated, and this leak falls away. So that's the trend of what we're seeing. Now, this is where it gets kind of interesting. Here, I'm showing a kind of a cartoon sketch. I think this is Oyster Creek, but there is here's your dry well head sitting up here, and it's beginning to leak in this bolted region, and gases, hot gases, are coming up, easily navigating the shield plug, lifting it if necessary, and accumulating in the reactor building. Now let's take a look at the composition of these gases. Here, at around 14 and a half hours or so, our calculation predicted the onset of head flange leakage. And so up until that time, this is the volume of air, hydrogen, steam, oxygen, and carbon monoxide, the mass accumulating in this upper reactor building. And you see initially it's mostly air or oxygen, a little humidity from the steam content, and certainly no hydrogen or carbon monoxide. But at the time that the head flange begins to leak due to overpressure, you can see some interesting things. What happens is steam begins to fill the reactor building, and the steam is also bringing with it hydrogen and carbon monoxide. So as these gases from the containment accumulate in the reactor building, the oxygen that was there, the air that was there, is being displaced. So you see the oxygen mass falls considerably, and the steam mass comes up to quite a high value. We'll come back to this, but basically with so much steam in the environment and so little oxygen in the environment, the mixture is not flammable. It's in the inflammable region. We refer to that as it's steam inerted. And the next picture kind of drives this home. I'm showing here this triangular picture here, which is the Shapiro flammability diagram, and it shows the constituents of the air either being hydrogen, steam, or air down here on this lower axis. And shown in this red envelope is the combinations of hydrogen, steam, and oxygen that would be flammable. Outside of this red zone, it's either has too little air or too little hydrogen or too much steam, and it's in a steam inerted condition. So prior to the containment venting operation, if you look over here at this curve, we have lots of steam, not much air, and a steady amount of hydrogen and CO, roughly corresponding to this steam inerted location on the Shapiro diagram. But as we begin to vent through the wet well vent, vent the PCV, the leak rate slows down, the hydrogen, and so what happens is the steam begins to condense because the flow of steam and into the containment has reduced. So steam begins to condense. The condensation of steam produces a partial vacuum. And so outside air begins to come back into the building. And so now you see we have hydrogen, increasing oxygen, and decreasing steam. And on the Shapiro curve, this begins to move towards the flammability region. As it happens, about an hour after venting was when the Unit 1 containment, not containment, reactor building exploded. And it seems very consistent with the trends of steam, hydrogen, and flammability conditions. So that's pretty fascinating outcome, I believe. Okay, so I hope you enjoyed that story on the hydrogen behavior in the Unit 1 reactor building. And now we're going to move on to some of the more intriguing, perhaps puzzling observations. These are modeling questions based on information that is emerging almost as we speak from the Fukushima re-entry, either by robots or other means. I want to just summarize quickly what information I'm basically drawing upon here. And let me move this over here. We're going to talk a little bit about this, BWR geometry, and the areas we're really interested in are the lower plenum and what is down now in the cavity following head failure. And what I can say here is the exploration of the Unit 2 and 3 containments are underway at a measured pace using robotic cameras, and they have revealed some intriguing and unexpected findings. First of all, you may not be aware of the muon examinations, but this is a pretty crazy high-tech methodology of imaging the entire vessel using cosmic muons from cosmic ray sources, and they have been able to perform crude imaging on Units 2 and Unit 3. And what the muon imaging seems to show is in Unit 2, in the lower head region, it looks very dense and seems to have significant mass of dense fuel debris still residing in the lower head. The comparable muon imaging in Unit 3 seems to have it seems to be comparatively voided of debris. Now, the other source of information are these robotic cameras and the examination of the dry well floor. And in Unit 2, it looks to be a very shallow, flat, solidified mass of material, and we strongly suspect it must be metallic. And then in contrast, a fairly massive accumulation of fuel debris in the Unit 3 cavity down in the bottom here, as well as some very sizable chunks of identifiable in-core structure. I just want to refer ever so briefly to this materials interaction chart. No doubt you've seen this. It's a famous chart. It's been around for quite some time. And it identifies some of the key melting points, such as pure melting point of UO2, zircaloy 4. But then there are these various lower melting point situations where we begin to have material interactions. We loosely refer to these as eutectic interactions, although there are monotectics and eutectics and paratectics, people will tell you. But these eutectics can have considerably lowered melting points, and we believe that some of these materials, such as the formation of iron zirconium intermetallics and so forth, could be playing a role in lower head attack by these molten materials. Let's take a look at what's in the bottom here. So in the flat debris layer of the Unit 2 cavity, this is kind of a close-up view of something recognizable in this amalgam of material down here. And it's actually the bail handle of the lifting handle of a fuel assembly. The engraved markings on here identify this as one of about 20 assemblies, but it's sitting down there intact, partially immersed in this resolidified material. Here is the concrete pedestal wall, and really no evidence of a melt attack is readily apparent here. And the flatness of this layer looks as though it was material that hit the floor, spread out, and froze. So how did that happen? That's our question. Of course, the computer codes do not model this degree of granularity. The next interesting observation comes from Unit 3. And here, down in the bottom, on this accumulation of debris in the cavity region, you see, I wouldn't exactly say virtually intact, but largely intact and definitely recognizable in-core components. This is the control blade drive tube and shaft that here you can see one in the normal location here, but now this virtually intact piece is lying, and there's several of these lying outside of the vessel. Now, this is hard to reconcile with code analyses because codes will generally melt all of this amalgam in the lower head and drop it down as a slurry of amalgamated material, not these segregation of identifiable large components. So we're puzzled, how did that happen? One other picture, I'm actually not sure if this is from Unit 2 or Unit 3, but here you can see in the bottom, again on this debris, here's a piece of the velocity limiter, the bottom end of the control blade. And here you can see it lying here on top of this debris. But now this material is down here in the lower vessel. So how did these large components get out, and how do we reconcile them with our code understanding? So I'm going to walk through a few pictures here that they're artist renditions. They're partly informed by code calculation tendencies, such as accumulation of metallic materials in the bottom of the head. That's what I'm showing here. And later accumulation of degraded fuel-bearing materials dropping into this lower pool of melt. So we're thinking it is possible that these intact structures could be left intact at the time that some of these potential chemical material interactions may be driving localized failure of the wall. This is definitely not in our current modeling suite. If you see text highlighted in blue here, I'm trying to put a little emphasis on it, and we think here that intermetallic reactions and the heats of mixing associated with these can be very exothermic and may be driving accelerated failure of the lower vessel wall. This picture here is intended to be a little further down the timeline, where more fuel-bearing materials are beginning to fall into the lower plenum. And as I mentioned, the metallic interactions forming an array of holes or penetrations in the lower head, allowing these metallic melts to fall out. And here I'm suggesting it's falling out of the vessel, it's hitting this lower CRD structure and falling through the grating. Here is one picture of where material looks like it fell through the grating below the vessel and begins to accumulate on the lower cavity. Since it's metallic and likely fully molten, it's going to have a tendency to spread across the bottom. And so I'm showing here a artist's suggestion of what happened in Unit 2. And we think that Unit 2 may have been arrested at about this configuration with a lot of debris, as suggested by the muon imaging, residing in the lower head, but mainly only the spread out metallic material sitting on the bottom of the cavity. So mostly metallic, and I have to say, no clear evidence of MCCI that was alternatively predicted by the codes. Think about Unit 3 as being further down the generic timeline of core degradation than Unit 2. Unit 2 was arrested, Unit 3 was not. And so what I'm suggesting here is that very likely that initially draining metallic melt is sitting down at the bottom, and now we have had actually fuel-bearing materials fall out of the lower vessel, again consistent with the muon imaging, and aggregate here in the bottom of the cavity, including some of these fantastically large intact pieces that have somehow slipped through the holes. We know very little about the holes through the gratings and the vessel at this point. They will be very clarifying in the future. But as I said, I'm personally viewing these two accidents as 2 points at different locations on the timeline. And I think I'm going to stop here on this topic here pretty soon, but I want to mention that this structure beneath the vessel does apparently interact with any melt that leaves the vessel these structures are quite massive and are basically not modeled in the severe accident codes, and kind of see that as a shortcoming in the long run. So let me just conclude some of the seemingly findings from the cavity inspection so far. And that is that it looks like the metallic core materials do look like they segregate from the ceramic fuel materials according to their melting points. And the code analyses do support these, growing conditions in the lower head. We think that these metallic mixtures might interact with the lower head through the material interactions and melting point suppression. Number of people are investigating these effects currently, and time will tell if that is not indeed the explanation for what we are seeing in these accidents. The head failure does seem to release intact core structures before those structures were grossly melted within the vessel. So there's a kind of a temporal segregation of core degradation that looks like it's occurring. And as I said, Unit 3 to me looks like it follows a similar degradation stages as Unit 2, just more extensive. And I'm going to qualify that to say we think. So I guess the question then becomes, do our current models need to capture the granularity of this kind of detail? And I think the jury is still out on that point. So I want to wrap things up here. It's been really great talking about all these memorable discoveries in the Fukushima discovery process, but I really have to speak briefly about uncertainty and variability. This is a whole workshop conference in and of itself, but let me just background here. So the phenomena and the physics that we study, there are uncertainties, and we may know these models to a certain degree, but we have to admit that there are uncertainties, for example, with oxidation rates, melting points, other potential rate processes that could be represented by code inputs, but we don't know exactly what the right number, if there is a right number. There are also sequence variabilities or even stochastic variabilities, such as safety relief valve failure, or do they seize open, or pump failures, or various operator interventions that could take place at differing times, other critical timing. So lots of places that variability can creep into ostensibly the same station blackout analysis. Throw in boundary condition variabilities, initial temperatures, heat sinks, and so forth, and there's a considerable amount of input definition uncertainty. So we often describe this situation as single deterministic, give me the best calculation, the one best calculation you know how to make, but I can come up with another equivalent calculation that will give you a different answer. Single deterministic analyses can't reveal cliff edge effects. Those can be missed, and the true uncertainty range of some of the outputs, maybe you're thinking you're okay with 800 kilograms of hydrogen, but what if it's 1200? And so uncertainty propagation can help you get a feel for how good is that number. This is kind of classically addressed through the Monte Carlo sampling process. I love the methodology. It is so easy to understand. And you would really like a distribution of answers as opposed to a single answer. here I want to show you just kind of schematically how that works. Let me get myself out of the way. This is quite a dated slide from some time ago, but this is how we did uncertainty propagation in Melcor. Like most codes, there is a rich user access to internal modeling parameters and ways to specify the boundary condition such that we can decide what are our uncertain distributions on some of the input properties, boundary conditions. We can represent those as distribution functions. We can Monte Carlo sample them, and then we can produce an ensemble, if you wish, could be 1,000 different input files that would produce, after execution of the code, 1,000 equivalent output files, all slightly different, all representing the uncertainty spectrum. And so now you have I'm showing here a cumulative distribution on the far right that tells you what the central tendencies are, can tell you what the 99th percentile might be, can tell you what the confidence intervals are. Very powerful methodology, and really something that must be accommodated in a something more than an exploratory, especially if you want to know how good are your answers. So in closing, let me just get this over here and say what we've been able to cover here are some notable real-world examples of some of the severe accident modeling nuances that we found to be pretty operative in the Fukushima analyses. Additionally, the analysis of the Fukushima accidents does provide us with some high-level, top-level integral validation of our ability to model these sequences, and I'm really quite encouraged with that. Nonetheless, there remain some significant mysteries concerning melt progression behavior in the lower head. This may be very BWR specific due to the large amount of zirconium in BWRs compared to PWRs. We're going to be studying those and try to decide if our modeling is good enough or if it needs improvement. I did want to close with that point. Uncertainty propagation is a crucially important aspect of severe accident analysis. And it's got to be one of the last skill sets adopted by severe accident analysts. But it's also a very liberating kind of experience to get a better feel for how good are your answers. Well, I hope you've enjoyed this discussion. Not too technical. My hope was to give you a feel for how the real world signatures look when we analyze them with a systems code such as Melcor. Hope you have some confidence. I want to wish you all good luck with your safety studies and in your individual endeavors. And with that, I'm going to conclude my presentation. I think there may be questions, but thanks for your attention, and we'll see you someday after the pandemic.
Thank you very much, Randy, and welcome. And many thanks for preparing this movie for us, and also for participating at the meeting now. Really appreciate it. And I know you're busy despite being retired. We have 10 minutes, 15 minutes for questions, and I will actually start with a question from Sebastian Besta. And he wrote me a letter or email since he wasn't able to access the chat. And he writes, "Hi, Randy. I'm very glad to see you participating in our seminar. Thanks for this excellent keynote lecture. I have a question about the development of Melkor after Fukushima Daiichi nuclear power plant related analysis. Were new developments and the code improvements planned?
And yeah, that's a good question, Sebastian. And I think we like to be optimistic that we will improve the codes as needed. It's always very much like a cost benefit, and often it's hard to demonstrate the actual need. If there is a regulatory issue that must be solved, then that's a stronger driver. And sometimes the scientific curiosity by itself is not sufficient. But I'm quite hopeful that as we come to appreciate better what actually happened, that code improvements will be invested. My particular interest is in, I think, an area that you're also interested in, and that is the material thermodynamics and material interactions that could be much more operative than we had appreciated.
And a comment on that, Randy, is that's one of the findings from TCOF, I guess you could say.
Right.
And I have another question from the chat, which goes in line with one of my questions. In which areas should we focus our research in order to understand the observations you showed in the lower dry well?
What was the question about the dry well?
What research areas should we focus our research in order to understand the observations? I guess it was the structures which were found and the big holes in the vessel penetrations. And if I may add to it goes with my question. If you were a research director and able to provide funding, and you wanted to increase the understanding of the behavior, which we saw there, what kind of experiment would you suggest?
Don't take me too seriously here, but I know that there were some experiments being considered in Japan, and maybe Sebastian has some ideas along this line. But if the material interactions indeed are what are failing the lower head, then we actually have no practical models to capture this, and so I think we're sort of at the stage of trying to define well-defined experiments that could lead to a practical model to predict a interaction with the head. Beyond that, I think we need to have more visual information from the exploration into the units to see no one knows what does the lower head look like right now. And so if it turns out to be a Swiss cheese of distributed holes or a giant hole, it may change our idea about what was truly operative and what research needs to be done.
Thank you. And I have another question from the audience, which in the chat. And may holes penetrations in the lower head come from interaction of P4C and stainless steel? That's something we studied early here in Sweden. So
there are so many. You recall the Hagen-Hoffman diagram of all those different potential material interactions, and there are so many of them. I think this is where interaction with the kind of scientific groups like TCOF, where they're building these databases and Gibbs energy minimization schemes and so forth to explore these. But where they, they're very scientific. They don't necessarily have a good connection with the, macro scale degradation in the core. And so I think we need to have good communication and coordination between groups like TCOF and then other groups trying to decide how should these phenomena be properly accommodated in the codes. It's still a discovery process.
Thank you. I also have a question from George Vazier, and he mailed me one. Randy, good to see you in this webinar, and thanks for an excellent presentation. Now, as SAMGs is usually built on the best estimate analysis, how would you like to see uncertainties, as you have discussed, addressed in it?
SAMGs is also such an interesting field, and I think there's more that could be done there. There was a day we had hoped that real-time running accident codes could be used to support decision making in SAMG. That seems to be still too elusive because of things like uncertainty. You just never know maybe the range of things. So one thing I had proposed before would be to rather like propagating uncertainty through the codes by the Monte Carlo process, that we could represent a SAMG action as it could go now. It could, an action could happen now. It could happen in 10 minutes. It could be more or less successful. And so by sampling methodologies, I think you could explore, the likelihood of success, or, the likelihood that pursuing this measure by this time period, you have, 80% of the cases, 80% of the runs are leading to a success, and 20% are not, or things of that sort. So almost in a PRA, probabilistic mode, you could explore these things beforehand to just get a feel for how effective is this approach. And I had hoped we could see some progress like that. I know that the Canadian regulator was kind of interested in that concept. I'd like to see that go forward.
I think that's interesting too. I have another question here from Walter Villanova. In unit number 2, it seems that vessel failure is highly non-central, as suggested, and hence the remaining substantial corium in the lower head is highly asymmetric and sits on the side of the lower head. Is this confirmed by the muon examination?
I'm not aware. That does ring a bell. That I believe that the suspected failure point is off to the periphery of the core, and so I guess that drives home the fact that the core degradation is not axisymmetric the way the computer codes model it. As far as the muon imaging goes, honestly, it's amazing that they can make use of cosmic rays to do this imaging, but it's still pretty shadowy. And in looking at the muon imagery, it's like a doctor reading a radiograph. It takes some experience to read that, and it all looks like smudgy dark stuff to me. So I can't really tell about the muon, but it does seem to be off center, as you say.
Thanks, and I agree. Difficult to interpret muon examination pictures, definitely. I have a question for you. What is the implication for the reactor safety of the things we saw in Fukushima with these big penetrations and the structures found in the containment?
So what are the implications? That's interesting. I think I'm still reaching for what it's definitely not what our codes are predicting, and it's a little hard. It's a little hard to speculate how important is that, except that it does sort of suggest that the failed ahead before you kind of generate these I don't know, highly degraded conditions in the lower head. In the PWR analog, you know, you often see these pictures of in vessel melt pool circulation, which that's going to require a long time for material sitting in the head to reach that configuration. And so it may be that some of these other more localized attacks could simply circumvent that. I mean, if these localized attacks are going to fail the lower head before you immerse even those control rod drive tubes into a amalgamated pool, well, it means that it's not the problem you thought it was. The head is not as much of a containment vessel as you thought it was. Now I'm really reaching, and I don't want to upset anybody's views about in-vessel melt retention or anything like that, but we're really trying to connect the dots and decide what is meaningful.
Thank you. I have also a question from Henry Gleneskog, which is a general comment, perhaps you could say, on most of the phenomena that took place at Fukushima were relatively well known, and we know that loss of cooling for many hours give a core melt. Nevertheless, most people were very confused when things went wrong. For instance, there were speculations if the explosions were caused by diesel being stored at a facility. Why do we have difficulties trusting our analysis? I guess
that's a good observation. You know, to many people who were watching the video streams before the Unit 1 reactor building exploded, it seems, you know, some people were thinking, oh, maybe the situation's going to be coming under control and everything is fine. Those people who have seen enough severe accident analyses should have known by 5 hours that something very bad was about to happen in Unit 1. But I don't know if it's hope springs eternal or what, you know, what it is. All of us who are researchers in severe accidents wonder why everyone does not find this so interesting and fascinating, but it's I
agree.
Yeah, there are many speculations, and you know, I went to Japan immediately after the accident, and honestly, the belief at the time was that Unit 1, they thought that one was the one where there was no problem, because they thought that the isolation condensers were cooling everything, and that Unit 2 was the problem. And in fact, as time played out, it was the opposite. Unit 2 went forever, almost avoiding meltdown, and Unit 1 was actually melted down by 6 hours.
Yes, thank you. I have another question here from Walter. Which part of the accident progression that requires significant effort and development in terms of modeling and simulation?
Yeah. Well, let's see. I think that as I kind of pointed out in my my illustration, the behavior in the lower head, we still have some mysteries there, and I probably won't be the one solving those, but that one seems to stand out. But another thing that is puzzling people is I believe there's a feeling that molten core concrete interaction was not as strong as maybe the codes had predicted. And, you know, the codes had been benchmarked against many experiments and will just generally predict uncoolable conditions in the cavity. And so in the, you know, in the OECD work, looking at the predicting the accidents, almost all the codes predicted protracted MCCI. And yet we're seeing, I think in Unit 2, we didn't see it at all. I think because we didn't get fuel down there. So that's a kind of a mystery. And Unit 3, I guess a mystery there is that, and the same thing for Unit 1, is that if MCCI did occur, we think we saw evidence of that in Unit 1, but perhaps we don't understand the radial versus axial erosion well enough, because we should have seen an attack of the cavity wall. And if the support pedestal had been eroded by MCCI, the vessel would have fallen, and we know it didn't happen in any of those cases. So I think we're struggling to kind of renormalize. We know that the physics are good, but apparently we may be over predicting the MCCI compared to what was observed in Fukushima.
Thank you. I just wonder if you could comment on Unit 1. What is the status there? The muon examination suggests there is no, in principle, no core in vessel. Is that right?
I don't know if I've seen a muon image for Unit 1, and I could have missed it. But the ones I've seen are for 2 and 3, I believe.
Yeah, I could be mistaken. Sorry.
Yeah.
But the current status is that there is no visual from the robotics in Unit 1, and we don't know much about Unit.
There was a small entry into Unit 1, I thought, but not nearly as, I think the conditions are just too difficult. The radiation levels are too high, and there's too much debris obstructing the robots, if I'm recalling this correctly. And so Unit 1 may be the last one that they get around to because of the dose rates.
Thank you. We'll check now. There's no further questions in the chat. So Randy, many thanks for attending this meeting, answering questions, and providing us with your observations. It was very valuable, and I really appreciate it. I hope to see you in real life soon when this pandemic is over, and I wish you good luck. You seem to be pretty, despite the retirement.
We're all waiting for our vaccinations, and likewise, I hope to see you all again someday in some pleasant venue. So thank you for inviting me, and it was my pleasure.
Thank you. And with that, I turn over to our chairman for ending this seminar. So please, Maurits.
Okay. Just a minute. Så, am I on air nu? Okej. Det har varit en lång dag idag. Mycket intressant att höra, så att jag ska försöka fatta mig kort, men Ni som har varit med tidigare när jag har startat och slutat och ni som var med igår vet väl att jag alltid kommer tillbaka till det här. En svart. Ett ögonblick, då ska jag försöka få till det. Då ska vi se där. Nu ska jag ha delat bilden.
Nej, jag kan inte se heller tyvärr här. Ska vi prova att jag delar åt dig, Maurits?
Ja, får nog göra det. För att jag kommer inte längre här nu, tror jag.
Nej, ska vi testa det? Jonas, funkar det? Se här, då ska jag göra så. Nu tror jag, Maurits, funkar detta för dig? Okej, jag gör så här, syns det något då? Nej.
Ja, det är ju en stund. Det är lite besvärligt utan bild.
Skumt.
Ja. Om jag ger dig kontrollen då, kommer upp bilden hos dig då? Så, då försöker vi igen. Det var trassel med min dator och det är nog bara inte datorn som är trött utan ni är nog ganska trötta också nu vid det här laget. Men jag vill ändå dra en repris om varför vi har suttit här i 2 dagar. Och det var ju så här att vår forskning om svåra haverier, de startade här med TMI 2. En nybyggd station, första härden och ett antal manuella felgrepp och dålig instrumentering gjorde att vi råkade ut för en härdsmälta. Den här olyckan, den ledde ju till att vi fick lite skrivningar i energipropositionen där Barsebäck skulle utrustas med filter och vi andra skulle avvakta och dra lärdom av Barsebäcksjobbet. Och det här ledde ju, som jag sa igår morse, om ni var med då, till filtra- och ramaprojekten där man tog fram den svenska strategin. Nu kan vi få nästa bild. Som då går ut på att vi inte försöker få stopp på härdsmältan i tanken utan vi släpper ut den och tar hand om den i inneslutningen och skyddar inneslutningen med filtrerad tryckavlastning och oberoende inneslutningsstrilar och sånt där så att man får ner riskerna för utsläpp. Vi har ju ett antal nyckelfenomen i det här och det är ju fortfarande hela haverisekvensen då, kylbarhet i tanken, hur går reaktortanken sönder, risken för ångexplosioner, fragmentering, kylbarhet av grusbädden och smälta betongreaktion som man måste hantera. Om vi tar nästa bild. Så när vi var färdiga här så fick vi ju ett villkor för fortsatt drift som jag påminner om lite då och då, att det går inte att stoppa den här forskningen om vi vill fortsätta köra, därför att vi har ett villkor på att vi ska fortsätta fortlöpande följa och värdera utvecklingsarbetet när det gäller svåra haverier och dra slutsatser om ytterligare säkerhetshöjande åtgärder. Och det här ledde ju då till att vi startade upp HAFOS-projekten, haveriforskningssamarbete, som gick i 2 år. Och sen hela APRI-serien. Då kan vi ta nästa bild. Där jag har då försökt att karaktärisera respektive projekt. Och som sagt, det är sent nu så att jag tänker då inte gå igenom APRI-projekten som sådana, men alla finns ju tillgängliga så att det bara går igenom det. Utan vi har HAFOS och till och med APRI 4 på den här bilden när man tittade på enskilda delar. Om vi fortsätter med nästa bild så har vi 5, 6 och 7 där det fortfarande är så. Vid APRI 6 så börjar vi försöka få tag på en helhetsbild av haveriförloppet. Eftersom allting hänger ihop ända från härdöverhettning till att grejerna ligger nere på botten av inneslutningen. Och det fortsatte då APRI 7. Om vi går vidare då till nästa bild. APRI 8, 9. Och nu APRI 10. Som är avslutat. Och om vi då tittar på resultaten vi har i det här så kommer det på nästa bild. Där det finns ett antal fenomen som vi då har sagt vi kan släppa. Återkriticitet, ett väldigt litet tidsfönster. Det var första APRI-projekten som sa det, att det finns ett litet tidsfönster där härden eventuellt är intakt och styrstavarna har smält. Men det tidsfönstret är så litet så det kan vi lägga åt sidan. Direct containment heating har vi också avfärdat. Vi har byggt upp ett ordentligt labb på KTH. Vi ser nu att hela haveriförloppet måste studeras sammanhängande. Och inte bara enskilda bitar utan man måste ha hela bilden. Ångexplosioner i reaktortanken. som kunde hota den och hota inneslutningen avfärdades på ett tidigt stadium. Ångexplosioner i inneslutningen är då inte helt avfärdat. Det är beroende på tankgenomsmältningsmod och mängden utrustning vi har under reaktortanken, framförallt på kokarna. Vi har fått modeller och beräkningsverktyg för analys av tankgenomsmältningen och vi har modeller och beräkningsverktyg för analys av hur vi formar en grusbädd i botten på inneslutningen. Vi har ett färdigutvecklat ramverk, RAM Plus, som ska knyta ihop alla dessa enskilda fenomen. Och om vi tittar på kemisidan så är det nästa bild. Där har vi då bidragit till modellutveckling för fissionsproduktkemin. Vi har specifika studier av haverikemi för kokarna. Jodbeteendet som enskild substans, det säger vi att vi har koll på nu. Vi har kartlagt organiska material och påverkan på haverikemin. Så nu är vi inne på tellur. Som enskild substans har vi det nu. Pågår det ju hur tellur interagerar med annat. Vi har tittat på ruthenium och har koll på rutheniums beteende som enskild substans. Så att vi har klarat av en hel del, men det finns en hel del kvar också som jag har försökt sammanfatta på nästa bild. Och nedsmältningsförloppet är det frågetecken på. Växelverkan mellan uran, zirkonium, järn, syre. Sammansättningen har påverkan på tankgenomsmältningsmoden som bland annat Randy pratade om. Vi vet ju inte mycket hur det är. Kylbarhet i tanken. Vi har en förståelse för förutsättningarna där, men det finns kvarstående frågor där. Och det påverkar förutsättningarna för en effektiv haverihantering och även då nästa frågeställning, hur går reaktortanken sönder? Och hur den går sönder, det påverkar ju i sin tur och styr då risken för ångexplosioner. Har vi kylbarhet i inneslutningen, får vi en tillräcklig fragmentering och spridning av grusbädden. Och som sagt, ångexplosioner i inneslutningen, det är beroende av tankgenomsmältningsmoden så att det inte är helt avfärdat. Och vi har kvar ett antal frågetecken när det gäller kemiska processer. Så att det finns en hel del kvar att göra i APRI 11 till att börja med. Vi har ett antal fokusområden där som jag har försökt skriva ner på nästa bild. Eftersom de termohydrauliska fenomenen är kopplade till varandra så måste då hela kedjan studeras. Alltså kylbarheten i reaktortanken, om den går sönder, hur den går sönder och hur en smältstråle eller nedfallande stelnade strukturer samverkar med drivdomsskogen på en kokare och hur det ser ut i nyckelhålet på en tryckare. Vi har risk för ångexplosioner som leder då till en mer eller mindre finfragmentering som styr kylbarheten i inneslutningen och risken för smälta betongreaktion. Kemiskt då så tittar vi under APRI 11 då på tellurs roll i det hela. Och om vi tar nästa bild så är ju då fokus för hela APRI-programmet då är att så långt det är möjligt verifiera den valda svenska strategin och att den är effektiv. Och om så inte är fallet så måste vi hitta alternativa åtgärder och APRI ska vara ett forum för teknisk vetenskaplig samverkan mellan myndighet och tillståndshavare och det ställer ju specifika villkor på vad vi kan ta upp och bearbeta i APRI. Så att APRI 11 projektet kommer då och fokusera på ett antal saker som vi tar i nästa bild. Där vi alltså ska samla information, stödja forskning och följa med svåra haverier för att få underlag för förändringar i kraftverken och få underlag till att förbättra och förändra rutiner och instruktioner för haverihantering. Vi har ju att få en bättre kunskap om hur mycket radioaktivitet som vi kan släppa ut, vilket då är avgörande för de beredskapsåtgärder som är planerade. Om vi tar nästa bild så har vi ett antal uppgifter som kommer att drivas i APRI 11. Och det är ju som jag sagt tidigare då. Vi tittar på hela sekvensen då, nedsmältningsförloppet i reaktortank, återsmältning, tankgenomsmältning, hur strukturer under tanken inverkar på sekvensen, ångexplosioner, specifikt då PVR-frågeställningar avseende då smältans spridning i nyckelhålet, den begränsade ytan som finns där. Vi fortsätter då att titta på haverikemin i reaktorinneslutningen och då i det här fallet då tellur just nu. Och naturligtvis så ska vi fortsätta följa upp olyckan i Fukushima Daiichi. Vi har ett antal internationella projekt som vi ska engagera oss i som vi har på nästa bild. Där då vi fortsätter då att ha kontakt med CESAP-programmet. Vi kommer att följa TEMIS som är då en fortsättning på TAI-experimenten som Christian pratade om. Ester och Rosau. Och naturligtvis så fortsätter vi att stödja forskningen om svåra haverier vid KTH och Chalmers. Så att så ser det ut i ett väldigt komprimerat format och då vill jag att du plockar fram sista bilden. Så vi i styrgruppen vill då till sist tacka våra moderatorer naturligtvis som hade stått med här om jag hade fått igång min delning av bildserien. Men moderatorerna ska ha ett stort tack för sitt jobb. Vi ska naturligtvis tacka alla föredragshållare för de intressanta presentationerna och alla ni som har varit med oss de här 2 dagarna. Och tack för visat intresse och hoppas att det har varit givande. Och hoppas att APRI 11-seminariet blir in real life, även om jag tycker det här gick väldigt bra. Så är det. Tack för mig och lämna över till Henrik.
Tack för det, Maurits. Normalt sett så skulle vi ju varit klara här. Men det finns vissa skäl till att jag inte låter Maurits få sista ordet den här gången. Nu delar jag skärmen här och tänker kolla här med våran tekniker om det syns någonting. Det funkar, vad bra. Då är det så här att jag upprepar lite grann snabbt här kort bara det som Maurits sa då, att ett stort tack till alla presentatörer, moderatorerna som har slitit hårt, gjort ett jättebra jobb. Tack till snabbmedia som har skött tekniken. Alla deltagare att ni har lyssnat. Och så vill jag tacka styrgruppen då. Och det är därför jag tar den här extra stunden. Jag hoppas ni har tid att sitta kvar och lyssna på det. Jag sa ju det allra första här på vårt webbinarium att styrgruppen förändrades en del under APRI 10-projektets gång. Och vi har några trotjänare som alltså har lämnat styrgruppen och kommer att lämna styrgruppen. Vi började med en styrgruppssammansättning där då Maurits var ordförande och så hade vi Margareta Tanse Larsson, Anders Henok, Staffan Dittmen, Patrik Isaksson, Ninos. Och 4 av dessa lämnar styrgruppen efter APRI 10. Och till att börja med Ninos, när jag började komma i kontakt med APRI när jag var doktorand, då var Ninos för mig den som var synonym med APRI och var han jag hade mest kontakt med. Och han framstod alltid som en väldigt trygghet för mig som doktorand och var väldigt uppmuntrande alltid. Ninos har också under väldigt många APRI-projekt fungerat som redaktör för slutrapporten. Gjort ett jättebra arbete med den. Ninos kommer inte gå i pension, men däremot så lämnar han styrgruppen. Så jag hoppas ändå att vi kommer fortsätta och ses i olika branschsammanhang framöver, Ninos. Men stort tack för ditt jobb. Margareta Tanse Larsson, Meta som vi brukar säga, hon har ju bidragit med väldigt mycket anläggningsperspektiv i styrgruppen. Hon har ju dessutom varit chef under hela sin tid i styrgruppen, alltså chef på Forsmark. Och det har varit ganska viktigt för oss. Hon har kunnat bidra med en hel del tydlighet och styrt upp vissa beslutsprocesser på ett bra sätt. Meta har alltid också månat väldigt mycket om våra forskare i projektet, inte minst de yngre forskarna, och verkligen velat att de ska ha bra förutsättningar för att kunna göra sitt arbete. En fin egenskap tycker jag. Meta gick i pension alldeles nyligen och jag tror att hon kommer att fördriva sina dagar mest på golfbanan i fortsättningen, både i Sverige och Sydafrika. Sen har vi Anders Henok. Och Anders, du var den som en dag för många år sedan tog emot mig på Ringhals när jag gjorde min första arbetsdag där nere. Du är ju då specialist i svåra haverier också, och du är och har varit länge styrgruppens orakel på det här området, kan vi säga. Oerhört kunnig i allt du gör som har med flödesberäkningar, koder att göra. Du har ett minne på det här området som är helt fenomenalt. Och du har alltid visat ett väldigt stort engagemang när du pratar om svåra haverier. Det uppskattas, det är en bra egenskap. Anders går i pension om ett litet tag, inte precis nu men om ett litet tag, och jag tror att du kommer ägna mycket tid åt att redigera diverse Wikipedia-artiklar. Ja, så har vi då Maurits Gärdinge, Mr. APRI får vi väl säga. Precis som du själv har berättat här så var det ju du och Emil Bachhoffner som en gång startade upp den här verksamheten, och du har ju varit den självklara ordföranden egentligen hela tiden här, va? Med en väldigt djup anläggningskunskap och dessutom en stor nyfikenhet på analysområdet. Och det där är inte helt vanligt att man är så kunnig både på skruv- och mutternivå, men dessutom kan resonera och diskutera saker om hur en Melkor-kod uppför sig, eller en MAP-kod, eller Gothic för den delen. Nästintill unikt skulle jag säga, och otroligt värdefullt för APRI. Du har aldrig heller varit partisk liksom i ditt agerande och liksom haft några särintressen som du har företrätt, utan alltid är det forskningen som har fått vara i centrum för det du gör. Och det är liksom inte att det ska tvingas fram några resultat för resultats skull heller, utan du har verkligen fått jobba för att forskningen ska få den plats den förtjänar, och det är en otroligt bra egenskap, det måste jag säga. Ett APRI utan Maurits, det är ju nästan inte ett APRI alls. Och vi får se hur det går. Säkerligen kommer en hel del saker behöva göras på annat sätt. Så blir det ju när man byter personer. Men tiden har sin gång. Du går i pension ganska så snart här. Och jag gissar att du kommer ägna mycket tid åt motorcyklar och diverse renovering på hus och liknande då. Så Maurits, Anders, Meta, Ninos, Ni har gjort ovärderliga insatser för APRI-projektet och jag vill bara säga ett stort tack och lycka till med allting som ni gör i framtiden. Och där fick vi rungande applåder från hela Kärnkraft-Sverige som ni hörde. Så med det så säger jag då tack för uppmärksamheten. Fortsätt att följa APRI-projektet på webben, apri.se. Och tack för uppmärksamheten. Ha en fortsatt bra dag allihop. Hej då.